The universe is constantly expanding, but how big can it truly become? Imagine a time when all the matter in existence was squished into an incredibly tiny dot, exploding across the cosmos in what we call the Big Bang. This mind-bending event has set the stage for billions of years of cosmic growth, unfolding through the invisible hand of dark energy and the dance of celestial bodies. Join us as we explore the limits of space, and if everything could end in a big burst. The universe is constantly expanding, a concept that has captured the attention of scientists since the early 20th century. Imagine blowing up a balloon. As you inflate it, every point on its surface moves away from every other point. This is a helpful way to visualize what happens in the universe. The space between galaxies grows, not because the galaxies themselves are moving through space, but because space itself is expanding. This expansion was first observed by astronomer Edwin Hubble, who noticed that galaxies are moving away from us and that the farther away they are, the faster they seem to be receding. This relationship suggests that the universe began from an incredibly hot and dense state around 13.8 billion years ago, a moment known as the Big Bang. This event marks the beginning of both time and space, setting everything in motion. One intriguing aspect of this expansion is that it's not just happening slowly and steadily. More recently, scientists discovered that the expansion is accelerating. This means that distant galaxies are moving away from us faster over time. To explain this unexpected behavior, scientists introduced the idea of dark energy, a mysterious force filling up the universe and driving this acceleration. Though dark energy comprises a significant portion of the universe, our understanding of it remains limited. Researchers continue to explore its implications and try to uncover the nature of both dark energy and dark matter, which together make up most of the universe's content. While scientists have made remarkable strides in understanding cosmic expansion, many questions remain, making this a vibrant field of study that continues to expand our comprehension of the universe. The discovery of the universe's expansion began in the early 20th century, reshaping our understanding of space and time. The first major clue came from the work of Edwin Hubble, an astronomer who studied distant galaxies. He observed that light from these galaxies was shifting towards the red end of the spectrum, a phenomenon known as redshift. This shift indicates that the galaxies are moving away from us. Hubble proposed that the farther a galaxy is from Earth, the faster it appears to be receding. This relationship implies that the universe itself is stretching, suggesting that it has been expanding since its origin. One key piece of evidence supporting this idea stems from the concept of the Big Bang. When scientists traced the expansion backward in time, they theorized that the universe must have started from a highly dense and hot state. To further validate this, researchers discovered what we call cosmic microwave background radiation. This faint glow, uniform across the sky, is a remnant from the early universe, confirming that it was once in a hot, dense state. Additionally, there are observations of galaxy clusters. When astronomers examine these clusters, they find that the distances between them are increasing over time. This ongoing expansion can be seen in the movement of galaxies relative to each other, supporting the idea that the universe is not static but dynamic and ever-changing. Together, Hubble's observations, the cosmic microwave background radiation, and the movement of galaxy clusters form a robust foundation for understanding the expanding universe. Each of these pieces of evidence reinforces the idea that from a singular energetic beginning, the universe has been growing and evolving into the vast cosmos we observe today. The concept of expansion is fundamental to our understanding of the universe because it provides insights into how everything we see around us has evolved over time. Imagine a balloon being inflated. The surface of the balloon represents the universe, while the dots on it symbolize galaxies. As the balloon expands, the dots move away from each other. This simple analogy helps visualize how the universe is stretching, with galaxies drifting away from one another, indicating that space itself is growing. This expansion relates directly to a pivotal moment in our cosmos known as the Big Bang. This is the event that marks the beginning of everything: space, time, matter, and energy. Recognizing that the universe has been in a continuous state of expansion since that moment allows scientists to piece together the history of the cosmos, tracing back to its origins and understanding how physical laws have shaped its development. Additionally, studying this expansion gives us clues about the fate of the universe. Depending on the effects of gravity and mysterious forces like dark energy, which fuels this expansion, we can make educated guesses about whether the universe will continue to stretch forever, eventually slow down, or even reverse course. Thus, the concept of expansion is more than a mere observation. It is a crucial key that unravels the past, present, and potential future of our universe, helping us to comprehend our place in the vastness of it all. The Big Bang marks the beginning of our universe, but understanding its origins requires diving into some fascinating concepts. Scientists believe that prior to the Big Bang, the universe existed in an incredibly hot and dense state, often referred to as a singularity. Imagine a point so small that it contained all the energy and matter that would eventually give rise to everything we see today. Approximately 13.8 billion years ago, this singularity underwent a rapid and dramatic expansion. This event is what we call the Big Bang. It wasn't an explosion in space, instead it was an expansion of space itself. Picture blowing up a balloon, where as you inflate it, the surface stretches and expands. In a similar way, space expanded instantly, creating room for time, energy, and matter to emerge. As the universe expanded, it began to cool down. In the first few moments after the Big Bang, elementary particles like protons and neutrons formed. As cooling continued, these particles clumped together to create atoms, primarily the simplest ones like hydrogen and helium. This gradual formation laid the groundwork for stars and galaxies. The expansion of the universe didn't just lead to the creation of matter, it also set in motion the evolution of the cosmos. As galaxies spread apart, the fabric of space expanded, causing what we observe today as the universe continuing to stretch. This ongoing expansion is a fundamental characteristic that scientists still study. Discovering it happens at an increasing rate, influenced by mysterious forces that govern the universe's behavior. The events believed to precede the Big Bang revolve around the transformation of an incredibly dense state into a rapidly expanding universe. This chain of events not only initiated the creation of time and space, but also set the stage for the diverse structures we see in the cosmos today. In the moments right after the Big Bang, the universe experienced an astonishingly rapid expansion known as cosmic inflation. Picture a balloon being blown up, but instead of a gentle increase, this expansion occurred at incredible speeds, far surpassing the speed of light. It happened within a fraction of a second, expanding from something incredibly tiny to a size much larger than our observable universe today. The concept of inflation helps explain several observations about the universe. One key piece of evidence is the uniformity of the cosmic microwave background radiation. This radiation fills the universe and serves as a faint afterglow of the heat from the Big Bang. Scientists have found that this radiation is remarkably smooth and uniform in all directions, suggesting that regions of space were once in close contact, allowing for even temperature distribution. Cosmic inflation accounts for this, as the rapid expansion would have stretched out any initial irregularities. Another compelling piece of evidence comes from the large-scale structure of the universe. The way galaxies are distributed today follows a pattern that supports the idea of inflation. These structures originated from tiny quantum fluctuations in the early universe, which were then exaggerated by inflationary expansion, leading to the galaxies and clusters we see now. Lastly, the observed rate of expansion of the universe today, known as the Hubble constant, also hints at this rapid early growth. By looking closely at the redshift of distant galaxies, astronomers can see how fast these galaxies are moving away from us, indicating how expansion continues on from the early moments after the Big Bang. Together, these observations create a compelling case for the idea that the universe expanded at astonishing speeds in its earliest moments, shaping everything we know about it today. The initial conditions of the universe were crucial in shaping how it has expanded over time. At the very beginning, right after the Big Bang, the universe was incredibly hot and dense. Everything was packed into a very small space. This intense state meant that energy and matter were in constant motion, creating a vast amount of pressure. As the universe began to expand, This pressure helped push everything outward, starting the process of expansion we see today. However, not everything expanded evenly. Tiny fluctuations in density occurred, meaning some areas had slightly more matter than others. These slight differences played a significant role in how galaxies and clusters of galaxies formed later on. Areas with higher density began to attract more matter due to gravity, causing them to slow down their expansion, stringing them together into the structures we recognize today. As the universe continued to expand, it cooled down. This cooling allowed particles to combine and form simple elements, primarily hydrogen and helium. The formation of these elements was key to creating the stars and galaxies that eventually filled the universe. Each of these steps depended heavily on the conditions present in those early moments. Additionally, the rate of the initial expansion influenced how fast galaxies moved away from each other. If things had been different, say, if there had been a lot more matter or energy in specific areas, the expansion could have slowed down significantly, possibly even leading to a contraction instead of continued expansion. Thus, the early state of the universe set the stage for its vast, ever-expanding existence and the structure we observe in the cosmos today. Hubble's law is a fundamental principle in understanding how our universe is expanding. Imagine the universe like a balloon being blown up. As the balloon inflates, every point on its surface moves away from the others. Hubble's law describes this very behavior on a cosmic scale. It states that the farther away a galaxy is from us, the faster it appears to be moving away. This means that galaxies that are very distant recede much quicker than those that are closer. This observation leads to a critical realization. The universe is not just static, but is continually expanding. Edwin Hubble, an American astronomer, made this discovery in the early 20th century by analyzing the light from various galaxies. He noticed a shift in the light that indicated movement. When light waves are stretched as an object moves away, it creates a phenomenon known as redshift, which resembles the way sound waves change in pitch as a siren passes by. The relationship between distance and speed of these galaxies forms the core of Hubble's law. It emphasizes that as the universe grows, it affects all galaxies and not just those closest to us. This expansion is not like an explosion from a single point, but rather space itself is stretching, carrying galaxies along with it. Understanding Hubble's law has been pivotal in shaping our view of the cosmos, confirming that our universe is dynamic, not static, constantly growing larger over time. Astronomers use redshift as a fundamental tool to understand how the universe is expanding. Imagine standing on a busy street and listening to the sound of a passing car. As the car approaches, the sound is high-pitched, but as it moves away, the sound becomes lower. This change in pitch is similar to what happens with light from distant galaxies. When a galaxy moves away from us, the light it emits stretches out, shifting toward the red end of the spectrum. This phenomenon is called redshift. By measuring how much the light is redshifted, astronomers can determine how fast a galaxy is moving away. The more significant the shift, the faster the galaxy recedes from us. This relationship allows scientists to create a pattern, linking the redshift of various galaxies to their distance from Earth. Next, they apply this understanding to the entire universe. When they observed many galaxies, they found that more distant ones had a greater redshift. This led to the conclusion that the universe is expanding. Galaxies are moving away from us and each other. By plotting the redshift against the distance of these galaxies, astronomers can calculate the rate at which the universe is expanding. This has profound implications, revealing not only how fast the universe grows, but also providing clues about its overall structure and fate. Essentially, redshift acts like a cosmic ruler, helping us measure the growth of our universe over billions of years. Telescopes have played a crucial role in unraveling the mysteries of the universe, particularly in understanding cosmic expansion. One of their most significant findings came from the observation of distant galaxies. These celestial objects emit light that has traveled vast distances to reach us, and when scientists analyze that light, they find something fascinating. It's shifting towards the red part of the spectrum. This phenomenon, known as redshift, indicates that those galaxies are moving away from us, which suggests that the universe itself is expanding. This expansion is not just a simple movement, It's happening everywhere in the universe, and telescopes have helped us measure its rate. By carefully observing how fast various galaxies are receding, scientists have determined that the universe is expanding at an accelerating rate. This unexpected discovery led to the creation of the concept known as dark energy, a mysterious force thought to be driving this acceleration. While we don't yet fully understand what dark energy is, its existence profoundly impacts our comprehension of the cosmos. Moreover, telescopes like the Hubble Space Telescope have provided essential insights into the age of the universe. By calculating the distances to certain types of stars and measuring how fast they're moving away, researchers have been able to estimate how long the universe has been expanding, leading to the conclusion that it is approximately 14 billion years old. The findings from telescopes have transformed our understanding of cosmic expansion from a mere curiosity into a fundamental aspect of cosmology, prompting questions about the future of the universe and the ultimate fate of galaxies. Each observation adds a piece to the puzzle, revealing a dynamic universe that continues to evolve before our very eyes. Dark energy is a mysterious force that is believed to be driving the universe apart. Imagine it as an unseen hand gently pushing galaxies away from one another and causing the cosmos to expand at an increasing rate. For a long time, scientists thought gravity was the only force at play in the universe, pulling everything together. However, observations made in the late 20th century revealed that not only is the universe expanding, but this expansion is accelerating, which was a surprising discovery. The term dark energy comes from the fact that it cannot be seen directly. It doesn't emit light or energy, and its exact nature remains one of the biggest puzzles in modern astronomy. It is thought to constitute a significant part of the universe, even more than the matter and energy we can observe. To visualize dark energy, think of a balloon being inflated. As the balloon gets larger, the points on its surface move further apart. Similarly, as dark energy pushes space itself to expand, galaxies move away from each other as if they are on the surface of a cosmic balloon. Understanding dark energy helps explain why the universe is behaving in this way, but exactly how it works is still unclear. Theories suggest it could be a fundamental property of space itself, or the result of new physics we are yet to discover. This enigma has led scientists on a quest to understand not just the fate of the universe, but the laws of nature at their most fundamental level. The more we learn, the more we realize that dark energy holds the keys to understanding the past, present, and future of our universe. The discovery of dark energy is a fascinating chapter in the story of our universe. In the late 20th century, astronomers began to measure the rate at which galaxies are moving away from us. Initially, they believed that the expansion of the universe was slowing down due to the gravitational pull of all the matter within it. However, in the late 1990s, two independent teams studying distant supernovae made a startling observation. Instead of slowing down, the universe's expansion is actually accelerating. This revelation was based on examining how the brightness of these supernovae compared to their distance. Supernovae are immense explosions marking the death of stars, and their brightness can act like a cosmic flashlight. When scientists looked at the light from these distant supernovae, they found that it was dimmer than expected. This suggested that these supernovae were further away than previously thought, indicating that the universe was expanding at an ever-increasing speed. To explain this curious acceleration, scientists proposed the existence of dark energy, an unseen force that acts throughout space, counteracting gravity and pushing galaxies apart. Observational evidence for dark energy extends beyond supernovae. The patterns of galaxies in the cosmic microwave background, radiation that fills the universe, along with observations of galaxy clusters, vividly support its existence. These observations help confirm that about 70% of the universe is composed of this mysterious energy. Even today, researchers continue to investigate dark energy, seeking to understand its nature and implications for the future of the universe. What we do know is that it reshapes our understanding of cosmic forces, reminding us how much we still have to uncover about the cosmos. Dark energy is a mysterious force that affects the very fabric of our universe, influencing how it expands over time. To grasp its impact, imagine blowing up a balloon. As you add air, the balloon expands, and the space between any 2 points on its surface increases. This simple act reflects what is happening on a cosmic scale, but dark energy is what drives this expansion. Currently, observations show that the universe is not just expanding, but that this expansion is accelerating. This means that distant galaxies are moving away from us faster and faster. Dark energy is believed to be the driving factor behind this phenomenon, working against the force of gravity, which tries to pull everything together. As dark energy continues to dominate the universe, several scenarios could unfold for its ultimate fate. One possibility is called the Big Freeze, where the universe continues to expand infinitely. In this scenario, galaxies drift farther apart, stars burn out, and the universe grows cold and dark over billions of years. As time progresses, it would become increasingly empty, with very few visible celestial objects, leading to a silent and desolate cosmos. Another possibility is the Big Rip. In this scenario, if dark energy continues to increase in strength, it could reach a point where it overwhelms all gravitational forces. This would result in galaxies, stars, planets, and even atoms being torn apart, leading to an end that is chaotic and violent. There's also a theoretical concept called cosmic equilibrium, where the effects of dark energy might balance perfectly with gravitational forces over vast timescales. In this scenario, the universe might achieve a steady state regarding its expansion, but that remains speculative. Dark energy plays a crucial role in shaping the future of the universe. It dictates the pace and nature of cosmic expansion, and depending on its properties, the universe could face a slow fade into cold emptiness, a chaotic end, or a stable, steady existence. These outcomes highlight how much we still have to learn about the forces that govern our cosmos. The cosmic microwave background radiation is often described as the afterglow of the Big Bang, the event that created our universe. Picture the universe as a hot, dense soup of particles, which existed just moments after the Big Bang. As the universe expanded, that soup cooled down, allowing particles to form into simple atoms. Eventually, this led to the release of light that has been traveling through space ever since, cooling and stretching as the universe continued to expand. Today, this light appears as microwaves, filling the entire universe almost uniformly. When scientists look at this radiation, they find a faint, even glow in every direction. This background noise is not only a remnant of the early universe, but also a treasure trove of information. It acts like a snapshot of the universe when it was just about 300,000 years old, providing essential clues about its temperature, density, and overall structure. Understanding this radiation is crucial for grasping how the universe has expanded over billions of years. By studying its temperature fluctuations, scientists can infer how matter and energy were distributed throughout the early universe. These patterns reveal insights into the rate of expansion, showing that the universe is growing faster now than it did in its early phases. This discovery has led to intriguing theories about dark energy, a mysterious force driving this acceleration. The cosmic microwave background is a key that unlocks the history of the universe, enabling us to trace its evolution from a hot, chaotic beginning to the vast, structured cosmos we see today. The cosmic microwave background radiation, often called the CMB, serves as a majestic backdrop to our understanding of the early universe. Imagine the universe shortly after the Big Bang, when it was a hot, dense soup of particles. As time progressed and the universe expanded, it cooled, allowing matter to form simple hydrogen and helium atoms. This transition marked a pivotal moment known as recombination, occurring about 380,000 years after the Big Bang. At that moment, photons, particles of light, could travel freely, unimpeded by the dense fog of particles that filled space prior. These photons are the very CMB radiation we detect today. They have been traveling through the universe ever since, allowing us to glimpse the state of the universe at that early time. When we study the CMB, we're examining this ancient light that tells us about the temperature fluctuations and density variations of the early universe. These tiny differences in temperature are like fingerprints of the universe's initial conditions, reflecting how matter was distributed shortly after the Big Bang. Scientists can analyze these patterns to deduce important information, such as the overall composition of the universe, including the proportions of dark matter, dark energy, and ordinary matter. Moreover, the The CMB provides a snapshot of the universe's geometry and expansion. The way this radiation is spread across the sky reveals insights about how quickly the universe is expanding and the forces at play during its evolution. By studying the CMB, researchers can piece together the timeline of cosmic history, helping us understand not just how the universe began, but also its ongoing journey toward the future. This ancient light is like a time capsule, revealing secrets of our universe's formative moments. Recent studies of cosmic microwave background radiation have provided crucial insights into the expansion of the universe. This radiation is a faint glow that fills the universe, a remnant from when the universe was just a fraction of a second old. Analyzing this radiation helps scientists understand the early universe's conditions and its subsequent evolution. One of the key findings from these studies is that the universe is expanding at an accelerating pace. This suggests that something unseen, often referred to as dark energy, is driving this expansion. Dark energy makes up a large portion of the cosmos and seems to exert a sort of pressure that pushes galaxies apart. The exact nature of dark energy remains one of the biggest mysteries in cosmology. The cosmic microwave background data has also updated our understanding of the rate of this expansion. Observations show that the rate might be higher than previously thought, which raises questions about existing models of the universe's evolution. When scientists compare measurements from the cosmic microwave background with other data, like that from supernovae, discrepancies become apparent. This difference hints that our understanding of cosmic evolution and the fundamental forces at play may need to be adjusted. The latest studies of cosmic microwave background radiation reveal not only that the universe is expanding, but also that this expansion is accelerating due to the influence of dark energy. Understanding these findings continues to reshape our view of the universe's past, present, and future. Cosmic inflation refers to a brief period in the very early universe when it expanded at an incredibly rapid rate. Imagine a balloon that, instead of slowly inflating over time, suddenly swells up dramatically in an instant. This rapid expansion happened within the first moments after the Big Bang, stretching distances in the universe by an enormous factor within a fraction of a second. This phase of inflation helps explain why the universe appears so uniform and homogeneous today, smoothing out any irregularities that might have existed. On the other hand, the general expansion of the universe is an ongoing process that occurs after inflation. It can be visualized as the universe gradually stretching over billions of years, like a raisin cake baking in the oven. As the cake rises, all the raisins move away from each other, and this is similar to how galaxies move apart over time in our universe. While inflation was a rapid event that set the initial conditions for everything, the general expansion represents a slower, continuous growth that has been happening ever since that early moment. Cosmic inflation was a lightning-fast expansion that smoothed out the early universe, while the ongoing expansion we see today is a more gradual process that continues to shape our universe into what we see now. Understanding both concepts provides insight into how the universe evolved from a tiny, dense state to the vast cosmos we explore today. The theory of inflation is a fascinating explanation that emerged in the early 1980s, designed to address several puzzling questions about the universe's early moments. To understand its origin, we need to go back to the Big Bang, which is the widely accepted account of the universe's beginning. This event suggests that everything we know started from an incredibly hot and dense state. However, as scientists examined the observable universe, they found some inconsistencies that traditional Big Bang theory could not easily solve. One key issue is the uniformity of the cosmic microwave background radiation. This faint glow fills the universe and appears almost the same in every direction, suggesting a high level of uniformity. However, traveling vast distances in space to different regions of the universe takes time, and there hasn't been enough time for these regions to interact and reach this uniform temperature. This leads to a second mystery: the flatness problem. When we measure the curvature of the universe, it appears remarkably flat. Without some form of influence to counteract gravity, the universe should either be open and expand forever or closed and collapse back on itself. Understanding why it is so flat is crucial. Inflation theory presents a solution by proposing that the universe underwent a rapid expansion just moments after the Big Bang. Imagine blowing up a balloon. Initially, the surface is small, but as you blow into it, it expands dramatically, smoothing out any irregularities. This quick expansion would stretch any initial inhomogeneities, leading to the uniformity we observe today. Overall, inflation theory is a significant breakthrough that offers answers to fundamental questions about the structure and uniformity of the universe, transforming our understanding of how the cosmos evolved from an incredibly small, dense point to the vast and intricate universe we see today. The theory of cosmic inflation suggests that the universe underwent a rapid expansion just after the Big Bang. This idea is supported by several lines of evidence that help scientists understand how the universe began and evolved. Firstly, the observed uniformity of the cosmic microwave background radiation plays a critical role. It is the afterglow of the Big Bang, filling the universe with a faint, even glow. When scientists measure this radiation, they find that it is remarkably consistent across vast distances, which is hard to explain without inflation. The rapid expansion would have smoothed out any initial irregularities, creating a uniform temperature and structure. Next, the distribution of galaxies and large-scale structures observed in the universe provides further support. Galaxies are not randomly scattered. Instead, they form clusters and filaments with vast empty spaces in between. The inflation theory explains how tiny fluctuations in density during the rapid expansion led to the growth of these structures. These small variations, which grew over billions of years due to gravitational attraction, match what we see today. Additionally, the theory predicts the presence of gravitational waves, ripples in the fabric of space caused by the rapid expansion. While detecting these waves is challenging, experiments are underway, and any positive results could bolster the inflation theory by providing direct evidence of the conditions present during the early universe. Lastly, measurements of the universe's expansion rate, known as the Hubble constant, have revealed discrepancies that are best interpreted through the lens of inflation. The predictions made by the inflationary model regarding how galaxies recede from each other align with observations, providing a coherent picture of cosmic growth. Together, these pieces of evidence create a strong case for cosmic inflation, shaping our understanding of how the universe transformed from a hot, dense state into the vast expanse we observe today. In cosmology, understanding the shape and nature of our universe involves addressing two intriguing puzzles known as the flatness problem and the horizon problem. Both of these issues stem from what we observe about the universe and its expansion. The flatness problem arises from the observation that the universe appears to be very nearly flat. When scientists look at the large-scale structure of the cosmos, the geometry seems to lean toward a flat plane, rather than being strongly curved either positively like a sphere or negatively like a saddle. This flatness suggests specific conditions regarding the overall density of matter and energy in the universe. If the density were slightly different in the past, the universe's shape would have evolved differently. However, the universe as we see it today maintains this flat geometry, which is surprising given how vast and dynamic it is. Now, the horizon problem is connected to how we see parts of the universe. In the early universe, regions of space were likely in contact with one another, allowing for the same temperature and density. However, today, we observe distant regions of the universe that are too far apart to have exchanged information or energy since the beginning of the universe. This creates a contradiction, as the vast distances imply that some regions should not have similar properties. The appearance of uniformity across the cosmos despite these separations leads to the horizon problem. Both of these issues are closely tied to the concept of cosmic expansion. The universe has been expanding since the Big Bang. As space stretches, it affects how we perceive distances and relationships between objects. This expansion has a significant impact on the evolution of the universe's structure. In the early moments of cosmic history, rapid inflation, an extremely quick expansion, could have smoothed out the initial irregularities, leading to the flatness we observe and allowing different regions to reach similar states before being pulled apart by ongoing expansion. This inflationary phase could also explain the horizon problem by providing a mechanism that allows disparate regions to share information about their conditions before being isolated. The flatness problem shows our universe to be remarkably even in its shape. while the horizon problem raises questions about how distant regions can share similarities. Both of these challenges are interlinked through the early expansion of the universe, suggesting that a rapid inflation phase could be key to understanding the state of our cosmos today. The theory of inflation provides a fascinating solution to some of the biggest questions in our understanding of the universe. Imagine the young universe as a tiny, extremely hot and dense point, and then suddenly, this point expands rapidly, much faster than the speed of light. This extraordinary growth happened in a fraction of a second, blowing up the universe from a size smaller than an atom to something vast and incredible. This rapid expansion addresses various problems that traditional models of the universe struggle to explain. One major issue is the uniformity of the cosmic microwave background radiation, which is a lingering afterglow from the early universe. If the universe only expanded at normal speeds, distant regions would not have been able to interact with each other. Yet we observe a remarkable uniformity across vast distances, a puzzle that inflation resolves by suggesting that all these regions were once close together before the inflationary period pushed them far apart. Another problem is the flatness of the universe. Measurements show that the overall shape of the universe is surprisingly flat, which means that the total energy density is very close to a specific balance. Inflation theory proposes that the exponential growth smoothed out any irregularities, leading to a flat universe. Lastly, inflation offers insights into the distribution of galaxies. Before inflation, the density variations in the early universe were small, but the rapid expansion stretched these tiny ripples into larger fluctuations. These fluctuations became the seeds for galaxies as they formed over billions of years. Inflation is a powerful idea that suggests a brief moment of extreme growth in the early universe. This concept helps explain why our universe looks the way it does today, solving issues of uniformity, flatness, and the formation of structure. The flatness and horizon problems are intriguing puzzles in understanding the early universe. These issues arise from observations that suggest our universe is remarkably flat and has a uniform temperature across vast distances, even when regions have not been in contact with each other since the beginning of time. Various alternative theories have emerged to explain these phenomena. One prominent alternative is the concept of cosmic inflation. This theory proposes that shortly after the Big Bang, the universe underwent an incredibly rapid expansion, much faster than the speed of light. Imagine blowing up a balloon. As you inflate it, the surface expands quickly in all directions, smoothing out any irregularities. In a similar way, inflation could explain why our universe appears so flat and uniform, as it stretches space itself over a brief period, allowing distant regions to become connected. Another idea involves the cyclic universe model. This theory suggests that our universe has undergone endless cycles of expansion and contraction. In each cycle, the universe would go through phases of being dense and hot, then expand and cool. Each transition would allow regions to exchange information, potentially smoothing out any irregularities and creating a uniform temperature. This model allows for a resolution to the horizon problem, since there would have been interaction among regions during previous cycles. A third approach is the multiverse hypothesis, which proposes the existence of many universes, each with different physical characteristics. In this view, our universe could simply be one of many, where the specific conditions of flatness and uniformity are coincidental outcome of random cosmic events. Each universe might have different laws of physics governing it, and we just happen to reside in a universe that exhibits these particular properties. These alternative theories provide fascinating perspectives that challenge our understanding of the universe's origins, seeking to explain why it appears the way it does. Each concept builds on ideas about space, time, and the very fabric of reality, pushing the boundaries of what we know and opening the door to further exploration in cosmology. The discovery of the universe's accelerating expansion changed our understanding of the cosmos dramatically. This revelation did not come all at once but unfolded as astronomers observed distant supernovae in the late 1990s. These supernovae are massive explosions of stars that occur under specific conditions. Scientists expected that the light from these explosions would follow a pattern, getting fainter in a predictable way as it traveled through space. However, to their surprise, researchers noticed that these distant supernovae appeared dimmer than anticipated. This unexpected dimness indicated that they were farther away than what the standard models predicted, implying that the universe was expanding at an ever-increasing rate. This groundbreaking discovery led to the proposal of a mysterious force driving the acceleration, which scientists termed dark energy. Before this discovery, the prevailing thought was that gravity, the force that pulls objects toward one another, would gradually slow down the expansion of the universe over time. The idea that the expansion was accelerating suggested that there was something counteracting gravity's influence on a cosmological scale. This shifted scientific perspectives from viewing the universe as a static entity to understanding it as a dynamic, evolving system influenced by forces that we are just beginning to comprehend. This new understanding not only opened up fresh avenues of research into the nature of dark energy, but also prompted a re-evaluation of existing models of cosmology, thereby transforming the landscape of modern astrophysics. The implications were profound. Our universe is not only expanding, but it is doing so with increasing speed, suggesting a far more complex and intriguing structure beneath what we see. The accelerating expansion of the universe is one of the most intriguing mysteries in modern cosmology, prompting several theories that attempt to explain this phenomenon. At the core of this mystery is the observation that galaxies are moving away from each other at an increasing rate, suggesting that the fabric of space itself is expanding more quickly over time. One leading explanation involves a mysterious force known as dark energy. This is thought to make up a significant portion of the universe's total energy content. Dark energy operates in opposition to gravity, causing galaxies to accelerate away from each other. Imagine a balloon being inflated. The surface of the balloon stretches outward as you blow air into it, while the dots on the balloon's surface represent galaxies moving apart. The precise nature of dark energy remains a puzzle, but its influence is fundamental to the universe's accelerating expansion. Another theory revolves around the concept of modified gravity. This idea proposes that the laws of gravity, as we understand them, may need to be adjusted at large scales. Instead of relying solely on Einstein's theory of general relativity, new models suggest that there could be additional factors at play, leading to effects that mimic an accelerated expansion. This could mean our current understanding of gravitational forces does not fully capture the dynamics of the universe on vast scales. Additionally, the possibility that the universe is expanding into an unspecified higher dimension has emerged as an intriguing perspective. If our universe is just a three-dimensional slice of a more complex universe, it could be that the additional dimensions cause peculiar gravitational effects, influencing the rate at which we observe the universe expanding. Ultimately, the accelerating expansion underscores the need for ongoing research and observations. While dark energy remains the most accepted explanation, alternative theories persist alongside our understanding, each contributing to the complex tapestry of cosmic evolution. As scientists gather more data from telescopes and space missions, our grasp of this phenomenon may evolve, shedding more light on what drives the universe to expand ever faster. Supernovae are crucial to unraveling the mysteries of our universe, especially in understanding why it's expanding at an increasing rate. When a massive star reaches the end of its life, it undergoes a spectacular explosion known as a supernova. These events release a tremendous amount of light, making them visible across vast distances. Because each supernova has a remarkably uniform brightness at its peak, astronomers can use them as cosmic beacons. By measuring how bright these supernovae appear from Earth, scientists can determine how far away they are. This distance can then be compared to the redshift of the light, which tells us how fast the universe is expanding as the wavelengths of light stretch due to this expansion. In the late 1990s, observations of distant supernova revealed something unexpected. The farther away these supernovae were, the fainter they appeared than expected. This observation indicated that not only was the universe expanding, but that the rate of this expansion was accelerating. The only explanation that could account for this phenomenon was the presence of a mysterious force called dark energy, which acts against gravity and drives the acceleration of the expansion. Thus, supernovae observations have not only provided key evidence for the expansion of the universe, but highlighted the complex dynamics at play, helping scientists grasp the fundamental nature of our cosmos. This knowledge pushes the boundaries of our understanding, uncovering the mysteries of dark energy and our universe's fate. The multiverse theory suggests that our universe is just one among potentially countless others, each with its own unique laws and constants. Imagine a vast landscape filled with bubbles, where each bubble represents a different universe. Our universe exists within one of these bubbles, which is continuously expanding. This expansion can be likened to the stretching of a balloon as it inflates, where every point on the balloon's surface moves away from every other point. As our universe expands, the multiverse theory proposes that other universes may also be forming and expanding, each perhaps experiencing its own version of reality. Some concepts of the multiverse arise from the idea of quantum mechanics, where every decision or occurrence creates a branching path leading to different outcomes, resulting in a new universe for each possibility. Additionally, cosmological theories about the Big Bang, which describes how our universe began expanding from a small, hot state, might also suggest that similar events could happen in other regions of space, leading to the birth of different universes, each with distinct properties. In this grand view, while our universe is expansive and dynamic, the multiverse concept opens the door to countless other realms, each with its own unique identity, waiting to be explored in the mind's imagination. Proponents of the multiverse theory suggest that the universe we observe may be just one of many, perhaps countless universes existing simultaneously. This idea stems from the understanding of cosmic expansion, which is driven by forces like dark energy, causing galaxies to move away from each other. When discussing cosmic expansion, proponents think about various ways this process might unfold, leading to different outcomes in different universes. One concept is that in some universes, expansion continues indefinitely. Here, galaxies drift further apart, leading to a cold and lonely cosmos where stars eventually burn out, leaving behind a dark void. In another scenario, some universes may experience a slowdown in expansion, possibly stalling after a while and resulting in a more stable universe where structures could form and endure longer. There are also scenarios where cosmic expansion reverses due to the gravitational pull of matter. In these universes, galaxies might begin to collapse back toward each other, possibly resulting in a big crunch. This could lead to new cycles of creation, possibly restarting the universe in a different form. By positing countless variations of these outcomes, multiverse proponents suggest that our universe's trajectory is just one thread in a vast tapestry where every possibility might be realized elsewhere. This not only expands our understanding of cosmic dynamics, but also our place within a much larger, interconnected reality. The multiverse theory suggests that our universe is just one of many, potentially infinite universes, each with different laws of physics and conditions. One of the significant challenges in proving or disproving this theory lies in the core issue of observable evidence. Most scientific theories rely on experimentation and observation, but cosmic distances make it nearly impossible to directly observe other universes. Unlike planets or stars, these alternate realities are beyond our reach, and we can't collect data from them in a conventional way. Another hurdle is the nature of the multiverse itself. If these other universes exist, they may operate under entirely different physical principles. This presents a complex situation where the traditional laws of physics as we understand them may not apply. As a result, even if we could glimpse another universe, it might not be in a format we can grasp or relate to scientifically. Moreover, the multiverse theory is often tied to concepts in quantum mechanics and cosmology, fields that already challenge our understanding of reality. The mathematics and theoretical frameworks that describe these ideas can become highly intricate, and drawing definitive conclusions becomes tricky. Scientists often find themselves dealing with speculative scenarios that require more assumptions than empirical data can support. Additionally, the philosophical implications of the multiverse add another layer of complexity. Questions arise about what it means for existence if there are countless variations of ourselves or realities. This philosophical aspect can diverge from the paths of science, leading to debates about whether the multiverse is a scientific hypothesis or a metaphysical idea. While the multiverse theory opens fascinating doors to contemplating existence and reality, the lack of direct evidence, the unique characteristics of other universes, intricate calculations, and philosophical ramifications make proving or disproving it a challenging pursuit for scientists. Dark matter is a mysterious substance that makes up a significant part of the universe, yet it does not emit or reflect light in any detectable way. It's like an invisible scaffold that supports the immense structures we see in space, such as galaxies and galaxy clusters. Scientists believe dark matter is responsible for a lot of the gravitational effects we observe. Without it, galaxies would not behave as we see them. They would spin apart, unable to hold onto their stars and gas. Imagine a galaxy as a rotating carousel. If you remove the anchors that hold it together but keep the visible decorations, the whole structure would scatter. Dark matter's gravitational pull acts like those anchors, helping to keep galaxies intact. Furthermore, dark matter plays a crucial role in the expansion of the universe. Early in the universe's history, right after the Big Bang, the distribution of dark matter affected how matter clumped together. This clumping is what led to the formation of stars, planets, and galaxies. As the universe continued to expand, the presence of dark matter influenced its rate of expansion. Observations indicate that the universe is currently expanding at an accelerating rate. This acceleration is linked to another mysterious force known as dark energy, but dark matter interacts with it by shaping the cosmic structure through its gravitational effects. The interplay between dark matter and these forces defines the universe's overall fate, guiding everything from galaxy formation to its ultimate destiny. Dark matter is a key player in the cosmic drama, influencing the structures we observe today and how the universe evolves over time. Detecting dark matter is a fascinating challenge since it does not emit or reflect light, making it invisible to our eyes and traditional telescopes. Scientists have developed ingenious methods to infer its presence. One key technique involves observing the gravitational effects of dark matter on visible matter, such as stars and galaxies. Imagine a carousel spinning in the dark. Even though you can't see the riders, you can tell they are there by the way they affect the motion of the carousel itself. Similarly, while we cannot see dark matter, we can notice how it influences the movement of galaxies. When astronomers study galaxies, they find that stars on the outskirts are moving much faster than expected. If only visible matter were present, they should be moving more slowly, like riders on the outer edges of a carousel. Their unexpected speed suggests that something else is exerting additional gravitational pull, likely dark matter. Another powerful method of detection comes from the cosmic microwave background. This is the afterglow of the Big Bang, a faint radiation that fills the universe. By analyzing tiny fluctuations in this background light, scientists can infer the distribution and amount of matter, including the elusive dark matter. These fluctuations serve as a natural blueprint of the universe's structure, revealing regions where mass is concentrated. Finally, researchers also create highly sensitive detectors aimed at capturing rare interactions between dark matter particles and regular matter. Though these events are exceedingly infrequent, if detected, they would provide direct evidence of dark matter. Thus, while it may be invisible, the gravitational and indirect signs of dark matter are plentiful, paving the way for deeper understanding of the universe's hidden components. Dark matter plays a critical role in shaping the universe and influencing its long-term expansion. To understand its implications, imagine the universe as a giant balloon. As this balloon expands, the material on its surface represents galaxies and stars. However, within the balloon are unseen structures holding everything together, much like dark matter does for our universe. While ordinary matter, such as stars and planets, only makes up a small part of the universe, dark matter is believed to constitute a significant portion. It doesn't emit light or energy, making it difficult to detect directly. Yet scientists know it exists because of the gravitational effects it exerts on visible matter. For instance, galaxies spin at speeds that wouldn't keep them together if only the visible matter was present. Dark matter provides the necessary extra mass to hold galaxies intact and ensures they don't fly apart. This presence of dark matter affects how the universe expands. The expansion is influenced by the combined gravitational pull of all the matter, both visible and dark. If dark matter were absent, galaxies would drift apart much faster than they currently do. Instead, the gravitational pull from dark matter acts like a stabilizing force, slowing the pace of expansion, especially at large scales. Furthermore, understanding dark matter helps scientists grasp the universe's fate. Current measurements suggest that while the universe is expanding, the rate of this expansion is accelerating. This acceleration is linked to dark energy, a mysterious force thought to be different from dark matter. Together, both dark matter and dark energy shape how structures form, evolve, and interact over cosmic time. Dark matter has profound implications for the universe's geometry, structure, and expansion rate. By influencing how galaxies cluster and behave, it plays a pivotal role in the cosmic story, profoundly impacting the future trajectory of the universe and our understanding of its ultimate destiny. The Big Crunch hypothesis presents a scenario for the ultimate fate of the universe, suggesting that the cosmos could eventually stop expanding and begin to contract. Imagine the universe as a balloon filled with air, where each section is moving away from the others as the balloon inflates. Currently, observations show that galaxies are drifting further apart, indicating that the universe is expanding. However, if the total amount of matter and energy in the universe is significant enough, this gravitational pull might dominate over the expansion. If that occurs at some point, the expansion could slow down, halt, and reverse. Picture the balloon starting to deflate. As it loses air, the material gathers tighter and tighter, leading to a collapsing state. As the universe contracts, galaxies would draw closer together, and enormous gravitational forces may lead to dramatic changes. Stars might begin to collide, and the cosmic structures we know could destroy each other in this new chaotic environment. Eventually, all the matter in the universe could converge into a singular point, where the laws of physics as we understand them may no longer apply, mirroring the conditions that theorists believe occurred at the beginning of time, the Big Bang. The Big Crunch envisions a cyclical universe, where expansion is followed by a recontraction, leading to a final state that is starkly different from the vast, spreading cosmos we see today. It raises fascinating questions about the nature of the universe and whether this process might happen only once or repeat in a series of cosmic cycles. The Big Crunch is a theoretical scenario about the future of the universe, where everything could eventually collapse back into a singularity. For this dramatic ending to occur, several specific conditions must be met regarding the universe's density and expansion. First, the overall density of the universe must be higher than a critical threshold. This density is a measure of the amount of matter and energy in space. Imagine the universe as an expanding balloon. If there is enough mass, the gravitational pull would be strong enough to stop the expansion and start pulling everything back together. This would require a certain amount of ordinary matter, and dark energy, which collectively influence the universe's fate. Next, the rate of expansion of the universe must slow down. Currently, the universe is expanding, and observations suggest that this expansion is actually speeding up due to dark energy. For a Big Crunch to unfold, this trend would need to reverse. Gravity would have to regain control over the expansion, resulting in a gradual slowing until it halts and then changes direction. Also, dark energy plays a crucial role in this process. If dark energy were to weaken or disappear entirely, the universe might be able to collapse. In this scenario, the attractive force of gravity would dominate, pulling galaxies, stars, and eventually all matter back toward a central point. For the Big Crunch to happen, there must be sufficient matter to halt the universe's expansion, a reversal of the current accelerating expansion, and a change in the behavior of dark energy, leading to a point where gravity eventually reigns supreme, causing everything to draw inwards. This fascinating possibility is just one of several theories about the ultimate fate of the cosmos. The Big Crunch is one potential scenario for how our universe might end. To understand it, let's first consider the universe's expansion. After the Big Bang, everything in the universe began spreading apart, like dots on a balloon as it's inflated. In the Big Crunch theory, this expansion doesn't last forever. Instead, imagine that the balloon starts to lose air and slowly begins to contract. Gravity pulls everything back together, and over an immense period, galaxies would merge, stars would collide, and galaxies would eventually squeeze into a singular point once more. This idea contrasts with other end-of-universe scenarios. One such scenario is the Big Freeze, where the universe continues to expand forever. In this case, galaxies drift farther apart, stars burn out, and the universe gradually cools down. Over billions upon billions of years, it reaches a state where no light or heat remains, resulting in a dark and cold cosmos. Another possibility is the Big Rip. In this scenario, the universe expands at an accelerating rate, driven by mysterious energy known as dark energy. As this expansion grows stronger, it could eventually tear apart galaxies, stars, and even atomic structures themselves, leading to a dramatic and violent end. The Big Crunch presents a cyclical view of the universe, where expansion is followed by contraction, potentially leading to another Big Bang and the start of a new cycle. In contrast, the Big Freeze depicts a universe that endlessly cools, while the Big Rip suggests a catastrophic ending driven by an uncontainable force. Each theory presents unique implications about the fate of everything we know, leading scientists to explore and debate these intriguing possibilities about the universe's ever-unfolding story. The heat death theory is a fascinating idea about the long-term future of the universe. Imagine the universe as a gigantic, ever-expanding balloon. As this balloon gets bigger, the gases inside spread out and the temperature drops. In a similar way, as the universe expands, everything within it, stars, galaxies, and even the very fabric of space itself, continues to move further apart. According to this theory, over an incredibly long time, the universe will reach a point where it can no longer sustain processes that require energy. Stars will exhaust their nuclear fuel, leading them to dim and fade away. Once all the stars have died, the universe will be filled with dark, cold matter, and the remaining energy will be too spread out to do anything useful. This scenario leads to a state of maximum entropy, where energy is so evenly distributed that there are no gradients to drive any physical processes. It's like a kitchen filled with a perfectly mixed bowl of ingredients. No matter how you try, you cannot create heat or energy from something that is uniformly mixed. In this stark and silent universe, even black holes will eventually evaporate over immense time frames. With no light, no stars, and no structure remaining, the universe will exist in a state of complete equilibrium where nothing much happens at all. This heat death signifies a universe that is cold, dark, and lifeless, a quiet, desolate end to the extraordinary journey of cosmic evolution. The heat death scenario emerges from the idea that the universe is expanding, potentially for eternity. As the universe expands, galaxies drift further apart. Imagine blowing up a balloon. As you inflate it, the dots on its surface move further from each other. In the vastness of space, this means stars will eventually exhaust their fuel and burn out, leading to a gradual dimming of the cosmos. In this scenario, as stars die and matter spreads thinly across an ever-growing universe, temperatures would cool. Eventually, even the remnants of stars will fade away, leaving behind only cold and dark remnants like black holes and subatomic particles. The universe would reach a state of maximum entropy, which is a measure of disorder or randomness. In simpler terms, everything would be spread out so thinly that no energy gradients would exist, meaning no more energy to do work or create organized structures. This constant or accelerating expansion also leads to a decrease in the availability of useful energy. For life as we know it to exist, energy flows are necessary. Think of them as currents that provide the drive for everything from stars shining to living organisms thriving. As expansion continues, these flows diminish, leading the universe towards a static state where all processes slow down or cease altogether. In the end, the universe would become eerily quiet, with no stars lighting up, no planets bustling with life, and no future events to unfold. The heat death marks the final chapter in the story of the universe, resulting from endless expansion and the inevitable march toward uniform emptiness. Scientists weigh the possibility of heat death and other end scenarios of the universe by meticulously examining the universe's evolution through theoretical models and observational evidence. To grasp this concept, we need to understand what heat death means. Essentially, it describes a state where the universe reaches maximum entropy, resulting in a uniform temperature and no usable energy to sustain processes or life. Imagine a room filled with an equal distribution of air. No areas are noticeably colder or warmer, leading to stagnation. To assess scenarios like heat death, researchers analyze the universe's expansion. By studying galaxies and how they are moving away from each other, scientists gather insights into the universe's fate. For instance, if the expansion continues to accelerate indefinitely, heat death becomes more plausible as energy becomes increasingly diluted. However, there are competing theories. The concept of the Big Crunch suggests that the universe might eventually stop expanding and start collapsing in on itself, leading to a highly energetic state before a potential rebirth. Alternatively, scenarios like the Big Rip propose that the universe might expand so rapidly that it tears apart matter itself, resulting in a violent end. Each scenario is evaluated through advanced mathematics and physics, allowing scientists to calculate probabilities based on current data. They consider various factors, such as the amount of dark energy and dark matter, both of which play significant roles in the universe's expansion and shape its destiny. By combining empirical observations with theoretical frameworks, scientists develop a clearer picture of how likely each scenario is, continuously refining their understanding as new discoveries emerge. The Big Freeze scenario presents a chilling perspective on the future of our universe. As the universe continues to expand, galaxies will gradually move farther apart, creating vast stretches of emptiness. Picture a balloon slowly being inflated. As it grows, the dots on its surface move away from each other. In the distant future, stars will burn out, and galaxies will drift into oblivion, leaving a dark, cold expanse. In this scenario, the energy in the universe becomes increasingly diluted. Instead of being filled with vibrant stars and lively galaxies, it will mostly consist of a sparse scattering of particles, predominantly hydrogen and helium, along with a little bit of dark matter. Over an incredibly long span, stars will cease to form, leading to a decline in cosmic activity. Eventually, even the remnants of once bright stars will fade, leaving behind only cold, blackened remnants. As time passes, temperatures will drop. The universe will edge closer to absolute zero, the point at which molecular motion nearly stops. While this may sound like a desolate ending, it's essential to understand that this transformation will unfold over trillions of years, far beyond our current understanding of time. The Big Freeze suggests that while the universe expands endlessly, it will gradually become a dark and quiet place, a stark contrast to the dynamic cosmos we witness today. The Big Freeze and heat death are concepts that both relate to the fate of the universe, but they describe different aspects of the end scenario. Let's start with the Big Freeze. Imagine the universe expanding like a balloon. As it stretches, galaxies move farther apart over an incredibly long time. This expansion continues, leading to a situation where stars gradually burn out and galaxies drift away from each other so much that they become isolated. This is the Big Freeze, a cold and dark universe where the remnants of stars and galaxies fade into silence. Everything will be so far apart that interactions will become rare, and it feels like time has slowed down drastically. On the other hand, heat death refers specifically to the state of maximum entropy in the universe. Entropy is a measure of disorder, and as the universe expands, energy becomes more evenly spread out. Over an immense timeline, all processes will reach a state where no energy is available to do work. Think of it like a car running out of gas. Eventually, it will just sit there, unable to move. In this scenario, every star will have exhausted its fuel, and all sources of energy will be depleted, leaving a lifeless and unchanging cosmos. So, while both concepts overlap in the lead-up to the end of the universe, the Big Freeze focuses on the cold and dark isolation that results from the expansion, while heat death emphasizes a state of complete uniformity and inactivity. Ultimately, the two are interconnected parts of a long cosmic timeline that envisions a universe where activity and energy dissolve into stillness. The Big Freeze scenario, often discussed in relation to the ultimate fate of the universe, is characterized by a continual expansion that leads to a gradual cooling and diminishing of energy throughout space. Several key observables can indicate that this scenario is unfolding. One of the most prominent signs is the measurement of the universe's expansion rate. Scientists have observed that galaxies are moving away from each other, and this trend has been accelerating over time. This acceleration is believed to be driven by a mysterious force they call dark energy. If this trend continues unabated, it suggests that the universe is heading towards a future where galaxies drift farther apart, effectively isolating them over immense distances. Another observable link to the Big Freeze is the cosmic microwave background radiation, a faint afterglow from the early universe. Analyzing this radiation provides insights into the universe's temperature. As the universe expands and ages, the heat from this radiation becomes diluted, resulting in lower temperatures. If ongoing observations show a steady decline in temperature over time, it would align with predictions of the Big Freeze. Additionally, the density of matter in the universe plays a crucial role. If future measurements reveal that the density remains below a certain critical threshold, it would indicate that gravitational forces will not be sufficient to halt the expansion. Instead, it would likely continue indefinitely, contributing to the Big Freeze scenario. Furthermore, examining the behavior of distant supernovae can offer crucial evidence. These bright explosions serve as beacons to measure distances in the universe. If their brightness continues to suggest a uniform acceleration in the expansion of the cosmos, that would reinforce the idea of an unattainable future where galaxies are no longer able to cluster together. Together, these observables provide a compelling picture of a universe that could be spiraling into an infinite state of coldness and isolation, devoid of interactions among celestial bodies over a vast timescale. The Big Rip theory presents a dramatic scenario for the future of our universe. It builds on the observation that the universe is expanding at an accelerating rate. Imagine the universe as a balloon that keeps inflating faster and faster. As this happens, if the force driving this acceleration, the mysterious dark energy, grows stronger over time, the consequences for everything in the universe could be catastrophic. In this scenario, galaxies would start to drift away from each other at an ever-increasing speed. The gravitational bonds holding galaxies together would weaken to the point of breaking. Eventually, the gravitational pull holding together clusters of galaxies would also falter, leading to their dissolution. This relentless expansion wouldn't stop there. Even the atoms within the stars could be torn apart. The forces pulling everything apart would become so strong that they would overcome all attractive forces in the universe. As the universe nears this endpoint, the fabric of space itself would seem to unravel. Star systems would face their doom, planets would be stripped from their orbits, and ultimately, everything that exists could be violently torn apart in a grand finale. This end, predicted by the Big Rip theory, emphasizes not just separation at great distances, but a fundamental alteration of matter itself, resulting in a universe where everything is reduced to individual particles or even smaller components. It's a reminder of how the expansive forces of our cosmos could one day culminate in a spectacularly chaotic destruction of everything we know. The Big Rip is a fascinating yet extreme scenario in the evolution of the universe. For this scenario to unfold, specific conditions related to dark energy must come into play. Dark energy, which makes up a significant portion of our universe, is thought to drive its accelerated expansion. For the Big Rip to happen, this dark energy would need to become stronger over time. Essentially, as the universe expands, the force of dark energy would increase, ultimately overpowering all other forces that hold matter together. Imagine a universe where everything is slowly drifting apart due to this intense dark energy. Galaxies would begin to separate, pulling away from each other at an ever faster rate. Eventually, the gravitational forces that hold galaxies, stars, and even planets together would be overwhelmed. This would lead to galaxies tearing apart, stars breaking free from their clusters, and even atoms being ripped apart at the most extreme level. The feasibility of the Big Rip is still a topic of active research and debate among scientists. Current observations indicate that while dark energy is causing the universe to expand faster, we do not yet fully understand its nature or whether it will continue to strengthen. Some models suggest a relatively stable form of dark energy, which would mean the Big Rip is unlikely. Others propose that its properties could change dramatically, making such a catastrophic end possible. While the Big Rip remains an interesting potential outcome for the distant future, it is currently uncertain. Thus, we continue to study the cosmos, seeking clues to better understand its fate and the forces at work within. During a Big Rip event, the fate of the universe hinges on the theory that the expansion of space accelerates to the point where all cosmic structures are torn apart. This scenario suggests that different kinds of structures would indeed experience varying effects based on their size and strength. Begin by considering galaxies, which are vast clusters of stars held together by gravity. In the early stages of a Big Rip, galaxies might still appear intact, but as the expansion force intensifies, the gravitational pull that binds them would struggle against this relentless stretching. Eventually, over enormous spans of time, the galaxy could unravel, stars flung from their orbits, losing their familial bonds. Now, as we shift focus to galaxy clusters, which are even larger aggregates of galaxies, a similar fate awaits them. Initially, they might resist the force of expansion due to their substantial collective mass, but if the Big Rip progresses, that structural integrity would also be challenged, leading to a gradual disintegration. On a smaller scale, consider planets. These bodies are held together by their own gravity. As the expansion force escalates, their intimate connections would ultimately succumb. Cracks would form, leading to fragments drifting away from each other, leaving behind barren fields of debris. Finally, zoom in on atoms and subatomic particles, which are at the tiniest levels of matter. Here, the Big Rip's effect would be even more pronounced. The fundamental forces that keep these particles together would be overwhelmed, causing them to tear apart at an atomic level. The very fabric that weaves reality would fray, leading to an existence devoid of structured matter. During a Big Rip event, cosmic structures experience a cascade of destruction that correlates to their size and the forces holding them together. From the grandeur of galaxies down to the intricacies of subatomic particles, each segment of the universe faces a grim fate under the influence of unchecked cosmic expansion. The cyclic or oscillating universe theory presents a fascinating idea about the life of the cosmos. Instead of viewing the universe as having a single beginning with the Big Bang, this theory suggests that our universe undergoes endless cycles of expansion and contraction. To understand this, imagine a balloon being inflated. As the balloon grows larger, it stretches out. When you let the air out, it shrinks back down. This is similar to the universe expanding and then collapsing back on itself. According to this theory, after a period of expansion, the gravitational pull of matter would eventually cause the universe to slow down and then reverse its growth. This contraction phase would lead back to a highly dense state comparable to the conditions just before the Big Bang. At this critical moment, the theory posits that a new expansion occurs, leading to the birth of a new universe, repeating the cycle. One key aspect of this idea is that it allows for the possibility of the universe being eternal, with no definitive beginning or end. The transitions between expansion and contraction might create a universe where new generations of stars and galaxies emerge, allowing different states of existence to unfold over time. While this theory proposes an intriguing model of cosmic evolution, it also raises many questions about the mechanics involved, such as how each cycle would be initiated and what physical laws would govern these processes. The search for answers continues, keeping scientists engaged in unraveling the mysteries of our universe's past, present, and future. To understand how a theory reconciles with current rates of expansion in the universe, we first need to appreciate what this expansion means. When we say the universe is expanding, we refer to the observation that galaxies are moving away from us, and the farther away a galaxy is, the faster it appears to be traveling away. This has led scientists to gather evidence supporting the idea that the universe has been expanding since its formation. The theory, often linked to concepts of cosmic inflation and dark energy, suggests that this expansion is not just happening gradually, but is accelerating over time. Picture blowing up a balloon. At first, you see the rubber stretching slowly, but eventually, as you blow harder, the rate of expansion increases. This is similar to what is happening with the universe. Current observational data, like the light from distant supernovae and the cosmic microwave background radiation, the afterglow of the Big Bang, suggest that the rate of expansion is indeed increasing. The theory holds that dark energy, a mysterious force that makes up a significant portion of the universe, plays a critical role in driving this acceleration. Think of dark energy as a force that pushes space itself apart, causing galaxies to move farther away at an ever-increasing pace. To reconcile the theory with observations, scientists employ detailed mathematical models and simulations that incorporate this understanding of dark energy and cosmic inflation. They compare predictions made by these theories with the actual data gathered from telescopes and space missions. By aligning the theoretical framework with observations of the universe's behavior, researchers can confirm or refine their understanding. This dynamic relationship between observation and theory allows scientists to paint a clearer picture of how the universe works. It demonstrates that as we learn more about the cosmos, theories can adapt, ensuring a deeper understanding of the ever-changing narrative of our universe's expansion. The idea of a cyclic universe, where the cosmos undergoes endless cycles of creation and destruction, appears in several historical and cultural narratives around the world. One of the most prominent is found in Hinduism, where the universe is believed to go through vast cycles known as kalpas. These cycles consist of periods of creation, preservation, and eventual dissolution. Each kalpa lasts for an immense time, and at the end, everything is absorbed back into the divine, only to rise again in a new cycle. Similarly, in ancient Greek philosophy, there were notions of an eternal universe influenced by thinkers like Heraclitus, who suggested that everything is in constant flux and that the universe has no beginning or end, only transformations. This idea resonates with the modern understanding of a universe that may expand and contract, reflecting a rhythm of existence. In Native American traditions, many tribes view time and existence as cyclical rather than linear. Stories and teachings often emphasize the circular nature of life, birth, death, and rebirth as part of a larger cosmic rhythm. This perception guides their relationship with nature and highlights the interconnectedness of all things. The ancient Mayans also had a cyclical view of time reflected in their calendar systems. They saw time as a series of repeating cycles, influencing their agricultural practices and cultural ceremonies. The Maya believed that these cycles governed the cosmic order of their world, creating a link between the celestial body's movements and their earthly existence. In addition to these specific cultures, the concept of return and renewal can also be observed in various myths and folk tales, where a hero or cosmic force undergoes trials and eventually returns to a state of harmony, signifying renewal and continuity. These narratives echo the notion of a cyclic universe, emphasizing the inherent rhythms found in both nature and existence itself. Such ideas reflect humanity's deep desire to understand the nature of reality, suggesting that the universe is not just an endless expanse, but also a dynamic system of birth, death, and rebirth. Quantum mechanics and cosmic expansion may seem like two separate domains, but they intersect in fascinating ways that help us understand the universe on both the smallest and largest scales. At the core of quantum mechanics is the idea that particles, the fundamental building blocks of matter, do not follow predictable paths, but instead exist in a state of probability. This behavior challenges our classical understanding of physics and introduces a level of uncertainty. Now, when we turn our attention to cosmic expansion, we are observing how the universe is stretching over time. After the Big Bang, the universe began to grow rapidly, and this expansion continues today. One crucial aspect of this process is the energy that fills the vacuum of space, which is where quantum fields come into play. In quantum field theory, every particle is seen as an excitation of a particular field that permeates the universe. For example, the electron is an excitation of the electron field. In the vast emptiness of space, these fields are still present, and they contribute energy even when no particles are created. This vacuum energy plays a significant role in cosmic expansion, leading to a phenomenon known as dark energy. Dark energy is a mysterious force that makes up a significant portion of the universe, driving the acceleration of its expansion. The connection to quantum mechanics lies in the idea that fluctuations in these quantum fields can give rise to vacuum energy, influencing how the universe expands over time. To put it simply, the tiny quantum world of particles and fields affects the large-scale structure of the cosmos. Just like the ripples in a pond can alter the surface, the dynamics of quantum fields influence the very fabric of space itself. This interplay may help explain not only why the universe is expanding, but also why that expansion is speeding up. Understanding these relationships is an ongoing journey, and it hints at the profound connections between the smallest entities of our universe and its vast, ever-expanding landscape. Quantum theory offers fascinating insights into the universe's expansion, especially when we look at the smallest scales of matter and energy. At these tiny dimensions, the rules governing the universe shift significantly. Instead of behaving in a predictable manner, particles begin to act in ways that challenge our conventional understandings. Imagine the universe as a constantly stretching fabric, where the largest events, like galaxies moving away from each other, are only half the story. When we zoom in to examine the fundamental particles, such as electrons and quarks, we encounter a strange and bustling world. Quantum theory tells us that these particles do not exist in fixed positions. Rather, they exist in probabilities, acting both like waves and particles. This peculiar duality implies that at any moment there is a chance to find these particles in various states and locations. Moreover, the energy fluctuations present in this quantum realm play a significant role in the overall expansion. Even in what is considered empty space, known as vacuum, there are fluctuations of energy that create virtual particles. This energetic backdrop could influence the rate at which space itself expands, merging the effects of quantum mechanics with cosmic evolution. When we consider the entire cosmos, applying the principles of quantum theory can help explain not only how the universe grew after the Big Bang, but also why its expansion seems to be accelerating today. Such acceleration hints at mysterious forces, often referred to as dark energy, which could intertwine with the principles of quantum fluctuations. Quantum theory provides a unique perspective, suggesting that the universe is not merely expanding silently, but is a dynamic arena where the smallest scales of reality interact continuously. This interaction not only shapes our experiences, but may redefine our understanding of time, energy, and the very fabric of existence itself. In the early universe, shortly after the Big Bang, everything was incredibly hot and dense. This dense environment was filled with energy, and within that energy, tiny fluctuations were constantly occurring. These fluctuations, known as quantum fluctuations, can be thought of as brief appearances and disappearances of energy in a vacuum. They are essentially the universe's way of showing some unpredictability at a very small scale. Now imagine these fluctuations like tiny bubbles in a boiling pot of water. Each bubble forms, grows, and then disappears. But in the early universe, these fluctuations were not just fleeting occurrences. Instead, they could have had significant implications for the overall expansion of the universe. When these tiny bubbles of energy became larger, they could have created small regions of varying energy density. As the universe began to expand, some of these varied regions influenced how quickly different parts of the universe expanded. Areas with slightly more energy than their surroundings could push outward more forcefully, causing those regions to stretch and grow faster than others. This effect contributed to what we see today, which is an uneven distribution of galaxies and cosmic structures. Furthermore, the rapid expansion of the universe during a period known as inflation could have been triggered by these fluctuations, leading to a brief but intense growth phase. During inflation, the universe expanded at an astonishing rate, which smoothed out much of the initial irregularities but also set the stage for the large-scale structures we observe now. Quantum fluctuations played a fundamental role in shaping the early universe's expansion by introducing variations that would influence the movement of matter and energy. These tiny ripples in the fabric of space and time set the groundwork for the complex universe we experience today. Gravitational waves are ripples in space and time created by incredibly energetic events, like the collision of two black holes or neutron stars. When these cosmic events happen, they send waves through the universe that can be detected on Earth, allowing scientists to gather valuable information. By studying these waves, researchers can learn about the properties of the objects that produce them, such as their mass and distance. This information is crucial for understanding the expansion of the universe because it helps us measure how fast the universe is stretching over time. As gravitational waves come from very distant events, they also provide a kind of cosmic perspective that light can't offer alone. For example, light from distant galaxies can be affected by the expansion of space, which may obscure or alter its path. However, gravitational waves travel unobstructed, allowing scientists to measure the universe's expansion directly and accurately. Furthermore, when gravitational waves are associated with events like supernovae or from the merging of neutron stars, they can serve as standard candles to better determine distances. This helps create a clearer picture of how fast the universe is expanding now compared to how it was in the past. By piecing together these observations, scientists can map out the history of cosmic expansion, revealing the universe's journey through time and providing insights into its ultimate fate. Gravitational wave astronomy has opened up an exciting new chapter in our understanding of cosmic expansion. Traditionally, astronomers relied on light from distant objects to measure how fast the universe is growing. However, gravitational waves offer a different perspective by detecting ripples in space and time caused by massive events, like two black holes merging. One of the significant discoveries came from observing gravitational waves associated with the merger of neutron stars. When these stars collide, they not only produce gravitational waves, but also release light in various forms, including gamma rays. By observing both the gravitational waves and the light that followed, scientists were able to calculate the distance to the event with great precision. This distance measurement, combined with the speed of the light we see, allowed researchers to refine the rate of cosmic expansion, known as the Hubble constant. This approach directly ties cosmic events to distance measurements in a more accurate way. The excitement lies in the potential discrepancies with previous measurements based solely on light signals from supernovae or other celestial objects. When gravitational waves are involved, it's like having a two-way communication, one through the invisible waves and another through visible light. The ongoing research into gravitational waves promises to deepen our understanding of the universe's expansion, allowing us to better grasp how quickly different parts of the universe are moving away from each other. This fusion of gravitational wave data with traditional astronomical tools is gradually reshaping our cosmic map, leading to more accurate models of the universe's history and its future. As this field evolves, we may soon uncover answers to fundamental questions about the nature of dark energy, the mysterious force thought to be driving the accelerated expansion of the universe. Discoveries in cosmic growth shed light on the powerful forces that shape our universe. These findings reveal the fundamental interactions between matter, energy, and gravity on a vast scale. Imagine the universe as a balloon expanding. As it inflates, galaxies and clusters move away from each other, which helps us understand the effects of dark energy, the mysterious force driving this accelerated expansion. By studying the distribution of galaxies and the cosmic microwave background radiation, we can map out how matter clumps together under the influence of gravity. This process, known as gravitational attraction, pulls matter into the dense regions that later become galaxies. Understanding this clumping behavior provides insights into the evolution of structure within the universe. Moreover, these findings assist in uncovering the role of dark matter, which is unseen yet essential. While we cannot see dark matter directly, its presence is felt through its gravitational influence on visible matter. Through various observations, scientists can infer how dark matter affects galaxy formation and clustering, revealing a web-like structure underlying the universe's expansion. Each discovery helps us piece together the cosmic puzzle. It enhances our understanding of how forces like gravity, dark energy, and dark matter interact and influence the universe's growth, painting a clearer picture of our cosmic environment and how it came to be. Grand unifying theories and theories of everything aim to create a cohesive understanding of the forces and particles that govern the universe. When it comes to cosmic expansion, these theories provide a framework for explaining how and why the universe is growing larger over time. To start, the universe began with the Big Bang, an event that set everything in motion. From that moment, space itself has been stretching and expanding, much like a balloon inflating. The exploration of cosmic expansion involves understanding the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Theories that attempt to unify these forces suggest that they were once a single force in the extremely hot and dense early universe. The role of dark energy is central to this expansion. This mysterious force acts like a sort of anti-gravity that accelerates the universe's growth. According to grand unifying theories, understanding dark energy may reveal insights into how the fabric of space behaves over tremendous scales. It pushes galaxies apart, changing the dynamics of their motion in ways that challenge our traditional views. One approach to developing a theory of everything incorporates quantum mechanics and general relativity, two pillars of modern physics that describe the behavior of the very small and the very large, respectively. Bridging these theories enhances our understanding of the universe's evolution. By connecting the behavior of particles to the curvature of space caused by gravity, scientists hope to explain not just cosmic expansion, but also how the universe may eventually evolve. Grand unifying theories and theories of everything strive to explain cosmic expansion by linking the fundamental forces of nature and the role of dark energy, ultimately aiming for a comprehensive understanding of the universe's past, present, and future. This is no small challenge, but it's one that could uncover the secrets of the cosmos and how it continues to transform. Developing a unifying theory of cosmic expansion presents several significant challenges. First, the universe itself is incredibly vast and complex, with elements behaving in ways that are often counterintuitive. For example, while we observe galaxies moving away from us, suggesting the universe is expanding, the exact mechanics behind this expansion aren't fully understood. One of the main hurdles is the role of dark energy, an unknown force thought to drive the acceleration of this expansion. It makes up a large part of the universe, yet its nature remains elusive. Scientists struggle to even define what dark energy truly is, whether it's a form of energy inherent to space, a property of gravity, or something else entirely. Each of these possibilities leads to different implications for how the universe expands. Additionally, the concept of cosmic inflation introduces another layer of complexity. This theory suggests that shortly after the Big Bang, the universe underwent an exponential expansion. Understanding how this rapid stretching relates to the ongoing expansion we see today is a crucial part of developing a cohesive theory. Another challenge arises from the tension between observable phenomena and the predictions made by existing theories, such as general relativity. While general relativity explains the gravitational interactions on a large scale, it does not account for the quantum effects present in very small scales. Bridging this gap between quantum mechanics and the behavior of large-scale cosmic structures remains a central issue for physicists. Moreover, observational data is sometimes inconsistent. Different methods for measuring the rate of expansion yield varying results, leading scientists to question if our understanding of fundamental aspects of the universe is complete. All these factors create a landscape filled with mysteries and uncertainties, making the quest for a unified theory not only challenging, but also a deeply fascinating endeavor in the field of cosmology. Scientists continue to gather data, refine their theories, and engage in discussions that may one day unravel the secrets of cosmic expansion, illuminating our understanding of the universe. The quest for a unified theory in physics is like chasing a thread that weaves through the fabric of the universe, connecting everything we observe. Currently, we have two primary frameworks: general relativity, which explains the forces of gravity and the behavior of massive objects like stars and planets, and quantum mechanics, which describes the intricate dances of tiny particles at the smallest scales. Each framework provides powerful insights, yet they seldom align comfortably with each other. Imagine discovering a unifying concept that brings these two theories together. It would be akin to finding a master key that opens every door in a vast mansion. Such unification could reshape our understanding of fundamental forces, allowing us to see gravity operating on a quantum level and offering new insights into the mysterious world of particles. With this greater understanding, our perception of the universe would shift dramatically. We would uncover deeper connections between the universe's workings, revealing a shared foundation for all physical phenomena. Entities once seen as distinct might be understood as aspects of a singular underlying reality. For instance, it could redefine our interpretation of black holes, the origins of the universe, and even the fabric of space and time itself. Moreover, this successful unification could ignite a philosophical revolution in how we view our place in the cosmos. We might start to see ourselves not just as observers of a vast universe, but as integral components of a grand interconnected tapestry. Questions about existence, purpose, and the nature of reality would gain new dimensions, leading to a richer dialogue about humanity's role in the universe. In this way, Finding a unified theory could transform not only the science of the cosmos, but our very understanding of what it means to be part of that cosmos. Next-generation telescopes and tools play a crucial role in deepening our understanding of cosmic growth and the evolution of the universe. These advanced instruments are designed to explore a wide range of phenomena, delving into the mysteries of galaxies, stars, and the very fabric of space and time. One of the most anticipated projects is the James Webb Space Telescope. It aims to observe the faint light from distant galaxies that formed shortly after the Big Bang. By studying this early light, scientists can gain insights into how galaxies grew and evolved over billions of years. This telescope focuses on infrared wavelengths, allowing it to penetrate cosmic dust and observe objects that are too cool or dim for other telescopes to see. Then there is the extremely large telescope, which features a mirror greater in diameter than any existing telescope. This impressive size will enable it to collect more light and provide incredibly detailed images of distant galaxies. It will offer a clearer view of the formation of stars and planetary systems within these galaxies, contributing to our understanding of cosmic growth. Additionally, a network of radio telescopes, such as the Square Kilometre Array, is being developed to study the universe's oldest signals. These signals can provide clues about the distribution of galaxies and the presence of dark matter, which is thought to make up a significant portion of the universe yet remains elusive. In parallel, advancements in gravitational wave detection offer another exciting avenue. By capturing ripples in space-time caused by events like black hole mergers, scientists can learn more about the dynamics of massive cosmic structures and how they interact over vast distances. Through these next-generation tools and telescopes, humanity stands on the brink of profound discoveries about the universe's past, present, and future. Each new insight will broaden our understanding of cosmic growth, ensuring that the quest for knowledge about the cosmos continues to inspire and challenge us. Technological advancements have a profound impact on our understanding of the universe's future expansion. As we develop new tools and instruments, we gain clearer insights into cosmic phenomena that were previously beyond our reach. For instance, when we improved our telescopes, we could observe distant galaxies and detailed features of their movement. This helps scientists measure how fast those galaxies are moving away from us, which is crucial for understanding the expansion rate of the universe. One significant area influenced by technology is the detection of dark energy. Dark energy is a mysterious force believed to be driving the acceleration of the universe's expansion. With advanced observation techniques, such as supernova surveys and cosmic microwave background analyses, researchers can better quantify the effects of dark energy and refine their theoretical models about how it operates over time. Each new discovery leads to updated theories. For example, when certain observations showed that the expansion of the universe is speeding up rather than slowing down, it prompted scientists to rethink existing models. This type of feedback loop, technology enabling new discoveries, which in turn adjust our theories, creates a dynamic progression of knowledge. Moreover, computer simulations have greatly enhanced our ability to predict future scenarios of cosmic expansion. By harnessing powerful computational tools, scientists can simulate the effects of various factors, such as the distribution of galaxies and the influence of gravity over billions of years. This allows researchers to visualize how the universe might evolve, including whether it will continue to expand indefinitely, eventually stop, or even reverse. Technological advancements are not just helpful tools, they reshape our theoretical landscape. As we continue to innovate, we unlock deeper mysteries of the cosmos, enriching our understanding of how the universe is expanding and what that means for its ultimate fate. Several upcoming missions and research projects are poised to enhance our understanding of cosmic expansion. One such initiative is the European Space Agency's Euclid satellite, which is designed to map the distribution of dark energy and dark matter across the universe. By examining how galaxies are distributed and how they move apart, scientists hope to uncover crucial details about the forces driving the universe's expansion. Another significant project is NASA's James Webb Space Telescope. Set to observe the oldest light from the universe, Webb will provide insights into the formation of galaxies and the early cosmos. By studying distant galaxies, researchers can determine how the expansion has changed over time, leading to a better understanding of the universe's evolution. In addition, ground-based observatories like the Vera C. Rubin Observatory in Chile are preparing to contribute valuable data. This facility will conduct regular surveys of the night sky, documenting how galaxies drift apart over time. Such comprehensive observations are vital for detecting the subtle changes in cosmic expansion. Moreover, various collaborations and experiments aim to refine measurements of key cosmic indicators, such as supernovae and gravitational waves. Tracking these phenomena helps scientists establish a clearer timeline of the universe's growth and acceleration. Each of these missions and projects collectively enhances our ability to peer deeper into the cosmos, providing insights that could reshape our understanding of cosmic expansion and the fundamental forces at play in the universe. Studying the expansion of the universe presents several intriguing challenges for astronomers and scientists. One of the primary difficulties lies in measuring vast distances. Since the universe is incredibly large, standard measurements are often inadequate. To overcome this, scientists use reference points, such as galaxies, to determine distance. However, accurately identifying and calibrating these references requires sophisticated techniques, which can introduce uncertainties. Another challenge is understanding the light emitted by distant objects. As galaxies move away from us due to the expansion, their light shifts toward the red end of the spectrum, a phenomenon known as redshift. This shift can vary greatly, complicating how we interpret the data. Observing these distant galaxies requires highly sensitive instruments, and even slight errors can lead to significant miscalculations. In addition, cosmic background radiation, the afterglow of the Big Bang, provides clues about the early universe, yet its detection is not straightforward. This ancient radiation is faint and must be separated from other sources of interference, like light pollution from our own galaxy. Moreover, the universe is influenced by various components, such as dark matter and dark energy, which are not directly observable. Understanding their roles in expansion involves complex theoretical models, adding another layer of uncertainty to our observations. As scientists continue to grapple with these challenges, they develop new technologies and methods to enhance our understanding of the universe's expansion, piecing together this vast cosmic puzzle. Astronomers face challenges when measuring the expansion of the universe. To ensure accuracy, they take several careful steps to address potential biases and limitations in their data. One major approach is utilizing multiple methods of measuring distance and expansion rates. By comparing results from different techniques like observing supernovae, clusters of galaxies, and cosmic microwave background radiation, astronomers can cross-check their findings against one another. This triangulation helps identify and correct for inconsistencies that might arise from a single method. Another critical factor is the selection of the objects being studied. Astronomers strive to choose a wide range of celestial bodies and ensure that they represent various types of galaxies and environments. This diversity helps prevent selection bias, where certain types of events or formations might skew the measurements if used exclusively. Additionally, astronomers pay careful attention to the instruments and technology used for these observations. Enhancements in telescope design and data analysis techniques have allowed them to gather more precise measurements over time. They also account for systematic errors, known factors that could influence results, such as how light behaves differently when passing through various cosmic materials. By understanding and correcting for these influences, they work to ensure that their findings are as accurate as possible. Finally, transparency in data and methodologies is essential. Astronomers share their findings and invite peer review to encourage scrutiny and validation from the scientific community. This collaborative approach helps ensure that any potential biases are caught and addressed before conclusions about the universe's expansion are drawn. Through these combined efforts, astronomers strive for a clearer and more accurate understanding of how the universe is growing. Current models of the universe's expansion are fascinating, but they are not without their puzzles. One major anomaly is the observation of the universe's accelerating expansion. Scientists expected a gradual slowdown of expansion due to gravity pulling galaxies together, but data reveal that this expansion is actually speeding up. This surprising behavior suggests a force acting against gravity, which we call dark energy. Yet dark energy itself remains a mystery, with no one fully understanding what it is or how it works. Another intriguing twist comes from the Hubble constant, which measures the rate of expansion. Different methods of measuring this rate produce conflicting results. Observations of the oldest light in our universe, produced shortly after the Big Bang, suggest a slower expansion compared to direct measurements of distant galaxies today. This inconsistency raises questions about our understanding of the universe's history and its expansion rate. Additionally, we've encountered the cosmic microwave background radiation, which is the afterglow of the Big Bang. This radiation provides crucial information about the early universe's state, yet some anomalies in its temperature fluctuations suggest that the universe isn't as uniform as we thought it to be. These irregularities challenge certain assumptions about cosmic inflation, the rapid expansion shortly after the Big Bang that is believed to have set the stage for our observable universe. Finally, there are the large-scale structures in the universe, like galaxy clusters. Their distribution does not fit neatly with existing models, indicating that we may be missing essential elements in our understanding of cosmic evolution. Each of these anomalies highlights gaps in our knowledge and points to the potential need for new theories or revisions of current models to better explain the mysteries of our universe. Speculative physics and futuristic theories have become essential components in our quest to understand the ever-expanding universe. At its core, cosmic expansion describes how galaxies move away from each other over time, a phenomenon first observed in the early 20th century. However, as scientists delve deeper, new ideas emerge, adding complexity to this initial picture. One significant concept is dark energy. This mysterious force seems to drive the acceleration of cosmic expansion. Imagine it as a hidden wind pushing galaxies apart, becoming more influential as the universe stretches. Speculative physics seeks to explain the nature of dark energy, considering whether it could be a constant force, if it's tied to the fabric of space itself, or if it might change over time. Another layer comes from theories like string theory and quantum gravity. These frameworks suggest that fundamental particles and forces might be interconnected in ways we have yet to fully comprehend. They propose that the cosmos could be made of tiny, vibrating strings or higher dimensional spaces. Such ideas could eventually shed light on how expansion relates to the fundamental structure of the universe. Then there's the exploration of parallel universes or multiverses. This exciting theory suggests that our universe might be just one of many, possibly expanding at different rates or even governed by different physical laws. If multiple universes exist, understanding their expansion could unlock insights into our own universe's behavior. Moreover, concepts such as inflation introduce a dramatic period of rapid expansion just after the Big Bang. This moment set the stage for the universe we see today. Investigating this period raises questions about how it relates to dark energy and current expansion. All these speculative ideas provide possibilities rather than definitive answers. They challenge scientists to think outside established frameworks, sparking new research and discoveries. As we engage with these theories, our understanding of cosmic expansion becomes more intricate and profound, reflecting the complexity and wonder of the universe itself. In the realm of fiction, many works have creatively explored the concept of the universe's expansion, often taking inspiration from real scientific theories, while also bending the rules of reality to ignite imagination. One notable example is the science fiction series, The Expanse. This story presents a universe where humanity has colonized the solar system, alluding to the vastness of space and the gaps between worlds as an essential aspect for exploration and conflict. While it captures the essence of humanity's urge for discovery, it reflects a more immediate and navigable expanse rather than the large-scale expansion scientists describe. Another significant piece is the novel Contact by Carl Sagan. Here, the notion of expanding space intertwines with the search for extraterrestrial life, positioning humanity within a broader cosmic context. Sagan's work emphasizes the idea that the expansion of the universe might hold clues for connecting with others, highlighting the continual search for knowledge amid an ever-growing cosmos. This mirrors scientific perspectives that emphasize curiosity about the expanding universe and the quest to understand our place within it. In the animated series Rick and Morty, the concept of an expanding universe is taken to whimsical and absurd heights. The show presents dimensions and realities that are constantly shifting and evolving, paralleling the scientific understanding of an ever-expanding universe. However, it offers an exaggerated, humorous take, prioritizing entertainment over precise scientific accuracy. Films like Interstellar also depict this theme effectively. In this film, the concept of gravity affecting time and space explores the idea of a universe that is not only expanding, but also influenced by the presence of massive objects. It presents a more nuanced interpretation, aligned with theories in physics, such as those proposed by Einstein, suggesting that time and space are interconnected and dynamic. Many fictional interpretations resonate with scientific understanding, exploring the profound implications of an expanding universe. While these works may take liberties for narrative engagement, they often reflect a fascination with the mysteries of space and humanity's unending pursuit of knowledge. Each story, through its unique lens, invites audiences to ponder the vastness of the cosmos and our collective journey within it, leaving room for both wonder and inquiry. Scientists are generally very open to reconsidering current ideas about the expansion of the universe when presented with new evidence or theories. The scientific method thrives on questioning established concepts and being willing to adapt our understanding based on new observations. For many years, the idea that the universe is expanding has been widely accepted, especially after the discovery of galaxies moving away from us. However, as technological advancements lead to new types of measurements, including the observation of distant supernova or the variations in cosmic microwave background radiation, scientists can gain fresh insights. If new theories emerge, like speculative ideas surrounding dark energy or modifications to gravity, scientists will rigorously test them against existing data. A theory that offers a better explanation or helps resolve current inconsistencies will attract serious attention. Revising ideas is not a sign of weakness, but rather a hallmark of a robust scientific field. It reflects the community's commitment to truth and understanding. Prominent researchers often engage with newer theories openly, leading to discussions in journals, conferences, or public forums. Such interactions foster an environment where knowledge evolves, allowing science to build on its past while continually seeking a clearer picture of the cosmos. The concept of an expanding universe has significantly impacted both philosophy and religion by challenging our understanding of existence and our place in the cosmos. Traditionally, many cultures viewed the universe as static and eternal, often paralleling their beliefs about creation and existence. However, the revelation that the universe is continuously stretching, growing ever larger since the Big Bang, reshapes these foundational perspectives. Philosophically, the notion of an expanding universe opens up questions about infinity, time, and change. If the universe is expanding, it suggests that everything is in constant motion and transformation. This idea leads thinkers to explore what it means to exist in a continually changing reality. It invites discussions about the nature of creation. Does the universe have a beginning? And if so, what occurred before that moment? Such inquiries challenge our previous understandings of cause and effect, pushing the boundaries of human thought. From a religious standpoint, the expanding universe can lead to a reassessment of creation narratives found in sacred texts. Some religious interpretations may struggle with the scientific view, as ancient texts often describe a fixed universe created once and for all. In contrast, the expanding cosmos suggests a more dynamic view of creation, which may resonate with some spiritual perspectives that see the divine as continuously active in the unfolding of reality. Moreover, this idea can provide a sense of connection to a greater whole. As people learn that we are part of an expansive universe, it can inspire feelings of solidarity with others and the universe itself. Many find comfort in the idea that humanity shares a collective journey through this vast, forever-changing space. Overall, the discovery of an expanding universe has opened a pathway for new interpretations and dialogue between science, philosophy, and religion, encouraging an ongoing exploration of what it means to exist in such a vast and mysterious cosmos. The concept of our universe being either infinite or finite carries significant socio-cultural implications that touch upon how we view our place in the cosmos. If we consider an infinite universe, it suggests that space and time stretch endlessly without bounds. This might instill a sense of wonder and humility within us. The idea that the possibilities of existence and experiences are limitless can inspire creativity, curiosity, and exploration. It invites philosophical questions about the nature of reality, existence, and our interconnectedness with all living things, encouraging collaboration and a shared quest for understanding. On the other hand, a finite universe implies that there is a defined limit to what exists. This can lead to a sense of urgency in how we treat our planet and resources, knowing there may be an end to everything we know. Such a perspective can promote stewardship of the Earth, as we might feel a responsibility to preserve it for future generations. Societally, it may provoke deeper reflections on mortality, purpose, and the legacy we leave behind. Communities might become more close-knit as the finite nature of existence fosters a greater appreciation for the time and experiences we share. Additionally, the discourse around whether the universe is finite or infinite can fuel various belief systems and spiritual ideologies. Different cultures may interpret these ideas through their religious or philosophical lenses, leading to diverse narratives about creation, existence, and the meaning of life. How we understand the universe profoundly shapes our societal values, relationships, and aspirations, highlighting the intricate bond between science and the human experience. Cultures around the world have diverse interpretations of the universe, especially concerning its expansion and ultimate fate. For many, the cosmos is not just a physical space, but deeply intertwined with cultural beliefs, mythology, and philosophical ideas. In ancient cultures, the universe was often viewed as a static entity, where the heavens were unchanging. For example, in various indigenous traditions, the sky was seen as a dome, with stars and celestial bodies placed by creators or divine beings. This perspective emphasizes harmony and balance, suggesting that the universe remains in a fixed state as a reflection of earthly life. As scientific understanding advanced, particularly in the last century, many cultures began to embrace new interpretations of cosmic expansion. The idea that the universe is continuously stretching was popularized by astronomers who observed the redshift of distant galaxies, indicating they are moving away from us. In Western scientific discourse, this led to the Big Bang Theory, explaining the universe's beginning and suggesting an ongoing evolution that might eventually lead to scenarios like a big freeze or a big crunch. Eastern philosophies, however, offer a different lens. In Hindu cosmology, the universe is viewed cyclically, where creation and destruction happen in repeated cycles rather than a straight line towards an end. This perspective welcomes the notion of cosmic expansion, while also incorporating a belief in eventual dissolution. African cosmologies often hold an interconnected view of the universe, where expansion may symbolize growth and change within the community and environment, rather than fear of an unknown end. This interconnectedness reflects a deep understanding of one's place in the cosmos, suggesting that humanity and the universe evolve together. In contemporary discussions, many cultures are expressing more curiosity about cosmic science, often infusing modern understandings with traditional beliefs. As they contemplate the universe's fate, questions about existence, purpose, and the potential for life beyond Earth blend scientific inquiry with spiritual and existential reflection. This encourages a richer dialogue on how humanity fits into a universe that is ever-expanding and dynamic, no longer seen as a distant and separate reality, but as part of a larger narrative that includes our stories, cultures, and the symbols we create. Mathematics plays a crucial role in understanding the expansion of the universe, acting as the backbone of many scientific theories. To grasp this concept, envision mathematics as the toolkit that scientists use to describe how celestial objects move and interact. One foundational theory is the Big Bang Theory, which posits that the universe began from a tiny, hot, and dense state and has been expanding ever since. To observe this expansion, scientists measure how far galaxies are from us and how fast they appear to be moving away. This is where mathematical formulas come into play. They help researchers quantify relationships, such as how the speed of a galaxy's movement is linked to its distance from Earth. This relationship suggests that the universe is expanding uniformly, much like dots on an inflating balloon move away from each other as it grows. Additionally, advanced mathematics allows scientists to create models of space-time, a concept that merges three dimensions of space with time into a single framework. These models help illustrate how gravity affects the fabric of the universe, influencing the rate of its expansion. For instance, Einstein's theories incorporate complex equations to predict how mass and energy will curve spacetime, and subsequently influence the universe's expansion rate. Mathematical tools, including calculus and statistics, enable scientists to analyze data collected from telescopes and other instruments. By interpreting this data mathematically, researchers can draw conclusions about the universe's past, present, and future. Through these calculations, they are able to suggest concepts such as dark energy, a force believed to be accelerating the expansion, which further demonstrates how mathematics connects observations with theoretical predictions about the universe's behavior. Mathematics is not just numbers and equations. It is a language that allows us to articulate the wonders of the cosmos, helping us decode the ever-expanding universe around us. To understand cosmic expansion, scientists rely on several key mathematical models that effectively describe how the universe grows over time. The foundation of these models rests in the concept of the universe's overall geometry and dynamics. One of the primary frameworks used is the Friedmann-Lemaitre-Robertson-Walker metric. This model simplifies the vast universe into a more manageable form by assuming it is isotropic and homogeneous, meaning it looks the same in every direction and at every point when viewed on a large enough scale. The FLRW metric provides equations that describe how the scale of the universe changes with time. Another important aspect of cosmic expansion is the cosmological constant, introduced by Albert Einstein. This constant is crucial when considering the effects of dark energy, which acts to accelerate the expansion of the universe. The mathematical representation of this constant in models explains why galaxies are moving away from each other at an increasing rate, a phenomenon observed through redshift measurements of distant galaxies. Cosmologists often use the equations derived from general relativity, which describe how matter and energy influence the curvature of spacetime. By applying these equations, scientists can simulate different scenarios of cosmic evolution. For example, they can model how the density of matter in the universe can lead to various possible fates of cosmic expansion, whether it will continue forever, slow down, or eventually reverse. Lastly, simulations of cosmic structure formation also play a role in understanding expansion. These simulations employ complex numerical methods to model the growth of large-scale structures in the universe, showing how galaxies and clusters evolve over time under the influence of gravity and dark energy. Through the combined use of models like the FLRW metric, the influence of the cosmological constant, equations from general relativity, and large-scale simulations, scientists can construct a clearer picture of cosmic expansion and the forces shaping our universe. Collaboration between mathematicians and physicists is vital in refining theories of the universe's expansion. The process begins with physicists observing cosmic phenomena, such as how galaxies move away from each other. They gather data and generate hypotheses about why and how the universe is expanding. Mathematicians play a pivotal role by providing the tools to analyze this data. They develop sophisticated mathematical models that describe the relationships between various cosmic elements, such as distance, speed, and time. These mathematical frameworks help physicists make sense of their observations and predict future events in cosmic expansion. As the collaboration deepens, feedback loops emerge. Physicists test the mathematical models against real-world data. If the results align, the models gain credibility. If not, they may need adjustment. This iterative process is essential for refining our understanding of the universe's expansion, leading to improved theories that explain complex phenomena, such as dark energy and the rate at which the universe is stretching. Ultimately, this partnership bridges the gap between abstract mathematics and practical physics, enhancing our grasp of the cosmos and revealing the underlying principles that govern its ever-expanding nature. Through this joint effort, both disciplines evolve, pushing the boundaries of what we know about the universe. Cosmic expansion is the phenomenon where the universe is constantly stretching, causing galaxies to move away from each other over time. This expansion is tightly linked to energy transitions and conversions, which are fundamental processes occurring throughout the universe. To understand this connection, we can think about how energy moves and changes form. In the earliest moments after the Big Bang, the universe was incredibly hot and dense, filled with high-energy particles. As the universe expanded, it cooled down, allowing energy to transition from one form to another. For example, when the temperature dropped, these energetic particles could combine to form simple atoms like hydrogen and helium. This transition was essential because as energy was released during this process, it contributed to the overall dynamics of expansion. Moreover, stars play a crucial role in this energy transformation. They fuse lighter elements into heavier ones, releasing vast amounts of energy in the form of light and heat. This energy not only creates the conditions necessary for life, but also affects the gravitational balance in the universe. The light from stars pushes against gravity, creating a counterbalance that influences how galaxies and cosmic structures evolve and expand. Additionally, the mysterious component known as dark energy, which seems to drive the accelerated expansion of the universe, is also tied to energy conversions. Dark energy is thought to be a constant energy field that affects the fabric of space itself. As space expands, this energy density remains constant, exerting an outward pressure that pushes galaxies apart even more rapidly. The energy transitions and conversions that occur from the initial moments of the universe up to present day shape not only the structure and elements we observe, but also the very evolution and expansion of the cosmos. The interaction of these processes results in a delicate balance of forces that continuously influences how our universe grows and changes over time. Thermodynamics, the branch of physics that deals with heat, energy, and how they interact with matter, plays a crucial role in our understanding of cosmic expansion. At its core, thermodynamics helps explain how energy affects the matter in the universe. As the cosmos expands, its temperature and density change, and this relates closely to the laws of thermodynamics. Imagine the early universe as a hot, dense soup of particles. As the universe began to expand after the Big Bang, it started to cool down, similar to how a pot of boiling water cools as it is taken off the stove. This cooling process is governed by the principles of thermodynamics. The laws dictate how energy transfers and how systems evolve over time, leading us to understand the behavior of cosmic matter as the universe expands. One important aspect is the concept of entropy, which is a measure of disorder in a system. As the universe expands, it becomes less dense and more uniform, increasing its entropy. This shift suggests that the universe is constantly evolving, moving toward a state of greater disorder. In cosmology, this increasing entropy is a sign that cosmic structures like galaxies and stars continue to change, impacted by the expansion. Additionally, the energy dynamics concerning dark energy, a mysterious force believed to drive the accelerated expansion of the universe, are also analyzed through thermodynamic principles. Researchers study how this energy behaves and its influence on cosmic growth. Understanding the balance of energy and matter, including how they interact and transform, is critical to unraveling the mysteries of the universe's fate. Overall, thermodynamics provides a vital framework for comprehending cosmic expansion, enabling scientists to make sense of how energy and matter evolve as our universe unfolds over billions of years. The conservation and dissipation of energy resources play a crucial role in predicting the long-term expansion of our universe. To begin with, energy in the universe is conserved, meaning that it cannot simply vanish, it can only change forms. This principle impacts how different parts of the universe behave over time. When we think about the expansion of the universe, we often relate it to the phenomenon known as dark energy. This mysterious force seems to be driving the acceleration of the universe's expansion. If energy resources are dissipated, such as through the heat death of stars or the eventual fading of even the smallest particles, this could alter the balance of forces that contribute to cosmic expansion. In a universe heading towards energy dissipation, we may envision scenarios where gravitational forces eventually dominate, slowing down or even reversing expansion. This situation is like a balloon losing air. As the energy resources dwindle, the structural integrity of the balloon is compromised and it slowly collapses. Conversely, if energy can be conserved through the processes within stars or other cosmic phenomena, there is a potential for continued expansion, albeit under conditions that may be different from what we experience today. This conservation might give rise to new mechanisms that could allow galaxies to continue receding from each other for a longer time. Ultimately, predictions about the future expansion of the universe depend heavily on how energy is conserved or dissipated. Understanding these dynamics helps scientists model different scenarios, leading to insights about the fate of everything from cosmic structures to individual galaxies and even the universe as a whole. The relationship between energy conservation and universal expansion provides a rich tapestry of possibilities for the future of our cosmos. In the vastness of the universe, cosmic expansion is influenced by various forms of matter and energy, some of which are still theoretical. One of the most discussed concepts is dark energy, an invisible force that seems to permeate all of space and drives the acceleration of the universe's expansion. Imagine a balloon slowly blowing up. As the balloon expands, dark energy supports that growth, pushing everything further apart. Another intriguing hypothetical form is dark matter. While it doesn't directly cause the universe to expand, dark matter contributes to the overall mass of the universe, influencing its structure and how galaxies move. You can visualize it as the unseen scaffolding in a building that holds everything in place, even though it's not something we can see with our eyes. Additionally, scientists have speculated about the existence of other exotic forms of matter, such as scalar fields. These fields could stretch across space and impact the universe's dynamics, similar to how ripples propagate through water when a stone is thrown. If scalar fields exist, they might behave in ways that accelerate or decelerate cosmic expansion depending on their energy density and interactions with other forces. Furthermore, there are theories about phantom energy, an even more mysterious form of dark energy that becomes more powerful as space expands. This concept suggests a future where expansion not only continues, but accelerates uncontrollably, potentially tearing galaxies apart. Picture a balloon that doesn't just expand, but does so faster and faster, growing without limit. As we delve into these hypothetical forms, it's important to recognize that they remain largely theoretical and are the subject of ongoing research. Each of these concepts helps scientists piece together the intricate puzzle of our universe, shedding light on the forces that dictate its history and fate. Exotic matter is a fascinating concept in physics that refers to materials with unusual properties, differing significantly from the common matter we encounter in our everyday lives. One of its most intriguing characteristics is its potential for negative mass. This means if you push it, instead of moving away, it could actually move toward you. This property opens up exciting possibilities for future space travel and even the expansion of the universe. Breakthroughs in understanding exotic matter could fundamentally change how we think about traveling through space and the very nature of our universe. For instance, if scientists can create or harness exotic matter, it might allow for the construction of advanced propulsion systems that could achieve speeds we currently think impossible. Imagine spacecraft that do not just travel at a fraction of the speed of light, but instead glide through the fabric of space by manipulating it. Moreover, the influence of exotic matter on expansion scenarios can shed light on the mysterious dark energy, a force believed to be driving the accelerated expansion of the universe. By studying exotic matter, researchers might discover new ways to interact with dark energy, potentially allowing us to control or navigate through the expanding cosmos more effectively. If we can understand how exotic matter could work with or against dark energy, it could lead to revolutionary technologies that enable us to explore distant galaxies or stabilize wormholes for easier travel. Breakthroughs in understanding exotic matter could unlock not only the future of space propulsion, but also provide insight into the fundamental workings of the universe. As we unravel these mysteries, the vision of humanity's journey through the stars may become more tangible than ever before. Throughout the history of astronomy and physics, scientists have made several intriguing observations that suggest there might be unknown forces at work in the universe. One of the most striking pieces of evidence comes from galaxies. Observations reveal that galaxies rotate at speeds which should cause them to break apart, given the visible matter we can see. However, they hold together, hinting at the presence of a mysterious substance referred to as dark matter. This unseen mass exerts gravitational pull, yet it has not been directly observed. Another fascinating observation involves the acceleration of the universe's expansion. In the late 20th century, researchers discovered that distant galaxies are moving away from us faster than expected. This unexpected acceleration points to a force that counteracts gravity, something scientists call dark energy. We don't fully understand what dark energy is, but it appears to make up a large portion of the universe, influencing its expansion. Moreover, experiments conducted with cosmic microwave background radiation, which is the remnant heat from the Big Bang, offer further clues. Analyzing variations in this radiation helps scientists understand the universe's early conditions and structure. The patterns observed suggest that the universe is not only composed of ordinary matter like stars and planets, but also influenced by these elusive forces. Together, these observations and experiments suggest a universe more complex than previously imagined, where unknown forces not only govern the behavior of galaxies, but also the fate of the entire cosmos. The search to understand these forces is one of the most exciting challenges in modern science. Cosmological theories provide different frameworks to interpret the same expansion data of the universe, which comes from observing distant galaxies moving away from us. These observations indicate that the universe is expanding over time. However, the reasons for this expansion can vary significantly depending on the theory applied. One widely accepted theory is the Big Bang model, which suggests that the universe began as a hot, dense state and has been expanding ever since. It explains the expansion in terms of the universe's initial conditions and its subsequent cooling. This theory aligns well with observations, as it predicts the existence of cosmic background radiation, an afterglow of the early universe, which has been detected. Another theory is the concept of cosmic inflation. Inflation posits that in the very earliest moments after the Big Bang, the universe underwent a rapid expansion that smoothed out discrepancies in its structure. This not only accounts for the observed large-scale uniformity of the cosmos, but also helps explain why the universe's expansion appears to be accelerating. On the other hand, alternative models, such as those involving modifications to gravity or the introduction of dark energy, modify the relationship between mass and the expansion. Dark energy is thought to act as a mysterious force causing the acceleration of the expansion. These ideas are still being explored and refined. Each theory, while using the same expansion data, emphasizes different aspects or mechanisms. By analyzing the way galaxies move and the light they emit, scientists can fit these patterns to various models. Such differing interpretations of the same data ultimately enhance our understanding of the universe. Each theory offers valuable insights, contributing to a broader picture of cosmic evolution. As new data becomes available, the theories will adapt and evolve, continuously shaping our comprehension of the universe. The diverse interpretations of the universe come with profound implications for our understanding of reality itself. Different cultures, scientific theories, and philosophies provide unique lenses through which we observe the cosmos. For instance, some cultures view the universe as a living entity, emphasizing its interconnectedness and the role of humanity within it. This perspective fosters a sense of responsibility toward nature and prompts questions about our place in the grand scheme. On the other hand, scientific interpretations focus on empirical evidence, seeking to unravel the mysteries of the universe through observation and experimentation. This approach has led to groundbreaking discoveries, such as the understanding of how stars form and die, or the way galaxies interact with one another. The scientific method relies on creating models that can be tested against reality, which propels our knowledge forward, but it can sometimes overlook the philosophical and emotional aspects of the human experience. These varying viewpoints create a rich tapestry of knowledge. They push us to ask deeper questions. What is the nature of reality? Are we merely observers or active participants in the universe? The implications are significant because they invite interdisciplinary dialogue, blending science with art, spirituality, and ethics. Each interpretation can guide humanity toward greater awareness of our collective existence and influence how we respond to challenges like climate change, technological advancement, or the pursuit of exploration beyond our planet. Ultimately, embracing these diverse interpretations allows for a more holistic view of the universe, one that combines wonder and skepticism, nurturing curiosity while grounding us in the tangible world. This synthesis of ideas leads to a deeper understanding of not only the cosmos surrounding us, but also our role within it, promoting a mindset that values both knowledge and wonder. Cross-disciplinary studies greatly enhance our understanding of expansion models in numerous ways. When researchers from different academic fields collaborate, they bring unique perspectives and tools that contribute to a richer analysis of complex problems. For example, physicists may focus on the fundamental forces driving the universe's expansion, while astronomers provide insights from observational data gathered through telescopes. Meanwhile, cosmologists integrate these findings to build models that explain cosmic events. These collaborations can also incorporate insights from fields like computer science, which enables the development of sophisticated simulations that visualize cosmic expansion. By working together, experts can address questions that no single discipline could fully answer alone. This pooling of knowledge fosters innovation in methodologies and interpretations, leading to more robust models. Moreover, interdisciplinary approaches allow for the exploration of new variables that may be crucial to understand cosmic expansion. For instance, the study of dark energy, a mysterious force accelerating the universe's expansion, can benefit from insights in both physics and philosophy, encouraging deep inquiries into existential questions about space and time. Cross-disciplinary studies not only enrich the data, but also foster a holistic view of the universe's expansion, leading to theories that are more detailed and comprehensive, ultimately deepening our grasp of how the universe evolves. Scientists have identified several key limits to cosmic expansion, which help us understand the universe's future and structure. One of those primary considerations is the density of matter and energy in the universe. Imagine the universe as a balloon being inflated. If the balloon has enough material, like the rubber, the expansion will slow down, potentially even leading to a reverse effect, where it might deflate. If there is insufficient material, the expansion will continue forever, and the universe will keep stretching until galaxies drift apart. Another important factor is the role of dark energy. This mysterious force is believed to be accelerating the expansion of the universe. Think of dark energy as a hidden hand pushing the balloon outward more aggressively as time goes on. Its presence complicates predictions about how expansion will behave in the long run. If dark energy remains constant, the universe could continue to expand without limit. But if it changes, the outcomes might differ. The ultimate fate of the universe is also tied to these factors. If the density of matter is above a certain threshold, the universe could stop expanding and begin contracting, possibly leading to a big crunch. On the contrary, if the current state persists, we may face a scenario where expansion leads to a cold and dark universe, often referred to as the heat death. Lastly, scientists also look at the cosmic microwave background radiation, which gives clues about the universe's behavior since its early moments. This remnant energy acts as a snapshot of cosmic conditions and allows researchers to measure how expansion has progressed over billions of years. All these elements combined slip into the rich tapestry of knowledge regarding cosmic expansion, shaping our understanding of the universe and its limits. The universe is continually expanding, a concept that has transformed our understanding of cosmology. To grasp how potential limits challenge or confirm these expansion theories, think of the universe like a balloon being blown up. As the balloon expands, the surface stretches and galaxies, like dots on that surface, move farther apart. Initially, this expansion seemed steady, but recent observations indicate it might not be so simple. Scientists have discovered that the universe's expansion rate is speeding up. This surprising twist introduces the idea of dark energy, an invisible force driving galaxies apart. Imagine if as you blow up the balloon, not only does it grow larger, but the air you're blowing in increases in pressure too. Dark energy acts like that, fueling the expansion and suggesting that there are limits to how much we can accurately predict. Now, if there are limits to this expansion, like constraints placed by the density of matter or energy in the universe, it poses questions about our current theories. Would these constraints lead to a slowdown, or might they allow for a continual acceleration? If, for example, the universe is approaching a maximum size governed by certain cosmic rules, that might lend support to theories like the cyclical model, where the universe expands and contracts repeatedly. The challenge lies in reconciling new discoveries with established theories. As researchers seek to understand these potential limits, they refine their ideas about cosmic evolution. Each new piece of data not only confirms aspects of expansion theories, but also pushes the boundaries, prompting scientists to rethink and deepen their understanding of the universe's grand design. Through this, we appreciate the dynamic nature of scientific inquiry, where every answer leads to new questions, ensuring that our pursuit of knowledge continues to expand just like the universe itself. Reaching the limits of the universe's structure and dynamics could radically change our understanding of how everything works. Imagine the universe as a vast, intricate web of galaxies, stars, and dark matter, all bound together by gravitational forces. If we were to hit a limit, it might imply that certain laws of physics as we know them could no longer apply. For instance, consider the expansion of the universe. Currently, we understand it's continuously stretching, with galaxies moving further apart over time. But if we reach a limit, this expansion could stop, reverse, or enter a new phase, altering the very fabric of space itself. It could mean that galaxies might start drifting closer together, leading to collisions and supermassive gatherings rather than isolation. Additionally, this would affect the energy balance within the universe. Certain parameters, like the density of matter and energy, play a critical role in determining the universe's fate. If we were to exceed or fall short of these thresholds, it could lead to different scenarios. One potential outcome might be a big crunch, where everything collapses on itself, while another could present a slow fade into darkness. These limits could also shed light on dark matter and dark energy, which together seem to drive much of the universe's behavior. Discovering the nature and potential limits of these mysterious components may open up new avenues of understanding, blending theories and observations in ways we have yet to imagine. Thus, reaching these limits could not only reshape the structure of the universe, but also fundamentally change how we perceive our place within it. Studying cosmic expansion has revealed profound insights about the nature of space and time. Imagine our universe as a vast balloon. As it expands, the surface of the balloon stretches, carrying points further apart. This visual helps us understand how galaxies are moving away from each other, indicating that space itself is expanding. This isn't just a movement through space, it's a fundamental transformation of space itself. From this expansion, scientists discovered that space and time are interconnected in a way that challenges our everyday experiences. When we observe objects in distant galaxies, we see light that left those galaxies long ago. This light takes time to reach us, allowing us to look back in time as well as out into space, a fascinating glimpse into the early universe. The rate of this expansion, which seems to be accelerating, leads us to the concept of dark energy, a mysterious force driving the speeding up of the universe's growth. This challenges our understanding of gravity, pushing us to re-evaluate how we perceive the forces at play over vast distances. Furthermore, the concept of space-time suggests that space and time are not separate entities, but part of a single framework. Events that occur are not just defined by their location in space, but also by when they occur, creating a richer understanding of reality. The study of cosmic expansion teaches us not only about the dynamics of the universe, but also suggests a deep and intricate relationship between space and time, leading us to explore dimensions of reality that are both fascinating and foundational to our existence. The expansion theory, particularly the idea that the universe is continuously growing, has significantly transformed our comprehension of gravity and other essential forces. When we observe distant galaxies moving away from us, it suggests that space itself is stretching. This realization compels scientists to rethink gravity, which was previously perceived mainly as an attractive force between masses. In this expanding universe, gravity plays a crucial role, pulling galaxies towards one another despite the backdrop of cosmic expansion pushing them apart. This duality creates a balance within the universe, where gravitational attraction counters the expansion driven by the energy within space, most notably, a mysterious form of energy referred to as dark energy. Moreover, as we delve deeper into the interactions between galaxies and cosmic structures, we also recognize that other forces like electromagnetism and nuclear forces behave differently under these conditions. For instance, while gravity is a long-range force, the effects of electromagnetism can vary widely depending on the scale and conditions. In a universe that is expanding, the relevance and strength of these forces can change, particularly over vast distances. The insights gained through expansion theory have also led to the idea that the behavior of fundamental forces may not be constant throughout the universe's life. As the universe evolves, the conditions under which these forces operate could transform, hinting at a complex and interconnected cosmic ecology. This understanding allows physicists to explore potential scenarios for the distant future of our universe, whether it continues to expand forever or eventually comes to a different fate. Ultimately, expansion theory has not only enriched our understanding of gravity, but has also invited us to view the universe as a dynamic tapestry, where all forces are intricately linked and where change is the only constant. Exploring these connections continues to be one of the most exciting frontiers in cosmology. The study of cosmic expansion teaches us valuable lessons about collaboration and exploration on a grand scale. As we observe the universe stretching and changing over time, we realize that no single person, country, or institution can understand these phenomena alone. Just as galaxies recede from each other, signaling a common origin, scientists across the globe come together to piece together the story of the universe. This collaboration is highlighted by international research projects and observatories where astronomers and physicists share data and insights. The need for diverse expertise is critical. Understanding cosmic expansion requires knowledge of physics, mathematics, and astronomy, all woven together by individuals from many backgrounds. This mirrors the idea that tackling significant challenges, whether in space or on Earth, often demands cooperative effort, transcending borders and cultures. Moreover, the exploration of distant galaxies promotes a sense of unity among humanity. As we search the night sky and measure the expansion rate of the universe, we are reminded of our shared existence on this planet. The vastness of space can foster humility, encouraging us to work together to address common challenges we face, such as climate change, resource management, and technological advancement. Ultimately, the journey to understand cosmic expansion illustrates that exploration is not just about discovering new worlds or laws of physics. It's also about bringing people together, nurturing curiosity, and advancing our collective understanding. In this unity of purpose, we find not only answers about the universe, but also a framework of collaboration that can help us tackle the challenges that lie ahead on Earth. The exploration of the universe's expansion is a collaborative effort that touches many scientific disciplines, with each contributing unique insights. Cosmology, the study of the universe's origin and evolution, raises fundamental questions that intersect with physics, astronomy, and even history. Physics plays a crucial role, particularly through the laws of gravity and thermodynamics. For instance, the concept of general relativity, a key theory in physics, explains how massive objects like galaxies influence the fabric of spacetime. This understanding helps cosmologists model how galaxies move apart from each other as the universe expands. By studying phenomena such as light from distant galaxies, physicists can measure how quickly these galaxies are retreating, leading to a deeper understanding of the universe's rate of expansion. Astronomy also provides invaluable observational data. Telescopes capture light from celestial objects, enabling scientists to gather evidence about their distances and velocities. By observing supernovae, which are massive explosions of stars, astronomers can determine how far away these events are and how quickly the universe is stretching out. This data feeds directly into cosmological models and helps refine our understanding of concepts like dark energy, a mysterious force driving the acceleration of the universe's expansion. Moreover, interdisciplinary work with fields like geology and archaeology helps trace the historical development of the universe. By studying the oldest materials on Earth, scientists gain insights into the conditions present during the universe's earliest years. This collaboration enriches cosmology by providing a timeline of events that guides current scientific endeavors. Even branches of mathematics are involved. Mathematical modeling is essential in creating simulations that predict how the universe behaves over time under various conditions. These models help visualize and understand complex interactions in the cosmos. The inquiry into the universe's expansion is not the work of cosmologists alone. It's a dynamic interplay of physics, astronomy, history, and mathematics, each field contributing to a richer understanding of the universe we inhabit. Together, they generate a comprehensive picture of cosmic evolution, making the exploration of our universe a truly collaborative and fascinating journey. Collaboration between the fields of biology, chemistry, and physics plays a crucial role in developing expansion theories, particularly when it comes to our understanding of how life exists and evolves in the universe. By merging insights from these disciplines, scientists can create a more comprehensive view of how cosmic and biological processes interact. At the core of expansion theories is the idea of how the universe is constantly growing and changing. Physics provides the fundamental laws that describe the movement of celestial bodies, the behavior of galaxies, and the forces at play in space, such as gravity and electromagnetic interactions. These principles help us understand the physical landscape in which biological processes might occur. Chemistry adds another layer of insight by exploring the building blocks of life. The interactions of atoms and molecules are essential to forming the complex compounds that create living organisms. By understanding chemical processes, scientists can infer how life might arise under different conditions, such as those found on other planets or in extreme environments. Biology, on the other hand, studies the mechanisms of life itself, how organisms develop, adapt, and change over time. Through the lens of biology, researchers can analyze how life might survive or even thrive in expanding spaces, such as on new planets or during significant environmental changes. When these fields collaborate, they can explore the possibilities for life in diverse conditions, including what it would take for organisms to adapt to new worlds. This interdisciplinary approach allows for more innovative solutions and theories, such as the potential for life in extreme environments, or the chemical pathways that could lead to new forms of biological existence. Overall, the interaction among biology, chemistry, and physics not only enhances our understanding of potential life forms in the universe, but also deepens our appreciation for the interconnectedness of life and the cosmos as it expands. Each field brings its unique perspective, creating a richer and more nuanced understanding of the universe we inhabit. Interdisciplinary research brings together different fields of study, creating a rich tapestry of ideas and perspectives that can lead to surprising discoveries about the cosmos. When scientists from fields like astronomy, biology, physics, and even art collaborate, they are combining tools, concepts, and methodologies that each discipline uniquely offers. This blend allows for new ways of thinking about old questions. For example, when astronomers study cosmic phenomena, they often rely on physics to understand the forces at work in different environments, like the life cycles of stars or the behaviors of galaxies. However, bringing in insights from biology can reshape our understanding. Consider how life on Earth adapts to extreme conditions. This knowledge can inform theories about potential life on other planets or moons where conditions differ dramatically from our own. Similarly, applying concepts from computer science like machine learning can enhance data analysis in astronomy. This allows researchers to sift through the vast amounts of data generated by telescopes and observatories to identify patterns that might not be visible at first glance. Unexpected correlations might be discovered, leading to new theories about how the universe expands or evolves over time. Cross-disciplinary work can also involve imaginative approaches, such as using art to visualize complex astronomical data. This creative perspective can make abstract scientific concepts more tangible and accessible, sparking new questions and ideas that might never have emerged from traditional scientific methods alone. Thus, when different disciplines engage with one another, they can uncover connections that revolutionize our understanding of cosmic growth, revealing a universe more intricate and interconnected than we previously imagined. Cosmic expansion refers to the way the universe is stretching over time, making galaxies move away from each other like dots on a balloon as it inflates. Right now, our view of this expansion is largely shaped by observing distant galaxies and tracking their redshift, which indicates how quickly they are moving away from us. However, as we look ahead to the next century, our understanding of this complex process may undergo significant changes. One major area of research involves dark energy, the mysterious force that is believed to be driving this accelerated expansion. Currently, scientists have limited knowledge about its true nature. Future advancements in technology and telescopes could provide clearer insights, allowing us to gather vast amounts of data from the universe's most distant corners. This may help us unravel the properties of dark energy, potentially leading to new theories about how it works and intersects with the fabric of space. Similarly, improvements in our understanding of gravity might reshape the theories surrounding cosmic expansion. Currently, we base much of our understanding on established theories, but new insights and discoveries could lead to adjustments or even complete shifts in our models. If we can study the gravitational waves, ripples in space caused by cosmic events, more effectively, we may uncover hidden layers of information about how materials in our universe interact during expansion events. Moreover, as new astronomical surveys begin to map the universe in unprecedented detail, we could discover new types of cosmic structures and phenomena that we have yet to observe. These observations might reveal more about how galaxies cluster and form, ultimately affecting our understanding of the universe's overall expansion rate. The next century could be a transformative period in cosmology. Advancements in technology, theory, and exploration may collectively enhance our grasp of cosmic expansion, allowing us to see deeper into the universe's past and future. With these breakthroughs, we might not only refine our current knowledge, but also uncover entirely new aspects of the universe that continue to intrigue and surprise us. The expansion of the universe is a fascinating topic that raises many intriguing questions. One of the most pressing inquiries is about the rate at which the universe is expanding, often referred to as the Hubble constant. Different methods of measuring this rate lead to conflicting results, leaving scientists puzzled about the actual speed of expansion. Understanding this discrepancy could uncover deeper insights into the underlying physics of our universe. Another significant question revolves around dark energy. This mysterious force is believed to be driving the accelerated expansion of the universe, but its nature remains largely unknown. What is dark energy? Is it a constant force, or does it change over time? These questions are vital in determining the fate of the universe. If dark energy prevails, could it lead to an eventual scenario where galaxies drift apart forever, ultimately leaving a dark and cold universe? Additionally, scientists are keen to explore the role of dark matter in this expansion. Dark matter is a substance that does not emit light, making it invisible and detectable only through its gravitational effects. How does it interact with regular matter and influence the expansion? Understanding the relationship between dark matter and the expansion could help paint a clearer picture of the universe's structure. There are also deeper questions about the laws of physics and if they remain constant over cosmic time. If our understanding of gravity or quantum mechanics is incomplete, the expansion of the universe might challenge what we think we know. Are there other dimensions or forces at play that we haven't yet discovered? Lastly, the origin of the universe and what came before the Big Bang remains a profound mystery. As we attempt to understand the expansion today, we inevitably ponder what conditions led to such an event. This curiosity spans not just our understanding of the cosmos, but also the very nature of existence itself. Each unanswered question tantalizes scientists and invites further exploration, pushing the boundaries of human knowledge and our understanding of the universe. Scientists' personal beliefs and interpretations play a fascinating role in unraveling the mysteries of cosmic expansion. It's important to realize that science is not just a collection of cold, hard facts. It is also influenced by the perspectives, backgrounds, and experiences of the individuals involved. When scientists contemplate the nature of the universe, their beliefs can shape how they approach problems and understand the data. For instance, a scientist who believes in the interconnectedness of all things might be more inclined to explore concepts that connect various cosmological phenomena. This perspective can inspire innovative hypotheses and creative ways to interpret data that others might overlook. As a result, their unique viewpoint might suggest new experiments or technologies that expand our capacity to study the universe. Moreover, there's a rich dialogue within the scientific community where different beliefs and interpretations collide and converge. This exchange fosters an environment of rigorous debate, pushing scientists to refine their theories and challenge each other's ideas. This process is essential for scientific progress. Each debate or discussion enhances our overall understanding of cosmic expansion as ideas evolve and are tested against observational evidence. In addition, personal beliefs can fuel the passion and curiosity that drive scientists forward. When a scientist is deeply interested in how the universe came to be and is motivated by a desire to share that understanding with the world, it can lead to groundbreaking discoveries. The emotions tied to personal beliefs might even inspire scientists to tackle complex questions that others find daunting. Thus, the interplay of personal beliefs and scientific inquiry creates a dynamic where new insights emerge, theories develop, and ultimately, our grasp of cosmic expansion grows richer and more complex. This ongoing quest is not just a pursuit of knowledge, but a shared human endeavor that reflects our diverse perspectives on existence itself.